Tonight we are going somewhere extraordinary. Not a place you can find on any modern map, not a city or a country or a landscape that any living human has ever walked through. Tonight we're going back across a distance of time so vast, so beautifully incomprehensible, that the word ancient does not begin to do it justice. Tonight we're going to the longest reign in the history of life on land, 165 million years, an age so long that everything you know, every civilization ever built, every language ever spoken, every song ever sung, every name ever carved into stone fits inside a single second of it. Tonight we are going to follow the dinosaurs. Not just from beginning to end, not just a summary, all of it. Every age and every landscape, every great transformation, every world they built and every world they survived. From their earliest, most uncertain beginnings, as small and overlooked creatures in the margins of a world owned by others, all the way through the golden ages of their greatest glory. The forests of giants, the oceans bordered by titans, the skies full of impossible flying creatures, all the way to the very last ordinary day before everything changed. This is their story, and it is one of the most beautiful stories this planet has ever told. So rest now, breathe slowly. You're perfectly safe and the journey is going to be long and quiet and wonderful. If you enjoy listening to sleepy prehistoric stories like this, please subscribe to the channel. New stories arrive every week, and there are many more ancient worlds waiting for you when you are ready. Before we can understand what the dinosaurs were, we first need to understand what the world looked like before they existed. Because the world they were born into was so radically different from the one we know today that it might as well have been another planet entirely. And to truly appreciate the full, staggering wonder of what the dinosaurs eventually achieved across 165 million years, we need to begin where they began. Small, overlooked, on the edges of a world that belonged to others. Picture the world 250 million years ago. Take a breath and let that number settle over you. 250 million years. Everything you have ever known, every civilization ever raised, every sea voyage, every painted cave wall, every carved stone monument, every written word and spoken language, every city ever built and every empire ever fallen. All of that history fits inside a window of time that is roughly 5 to 10,000 years long, depending on how generously you measure it. Against 250 million years, the entire recorded history of our species is thinner than a single page in a book that fills a warehouse from floor to ceiling. 250 million years ago, the world looked almost nothing like the one you live in now. There were no separate continents as we know them, no Atlantic Ocean, no Pacific as we recognize it, no Mediterranean cutting its blue path between ancient shores, no Indian Ocean, no Arctic Sea. Every piece of land on the surface of the Earth had been assembled over hundreds of millions of years of slow geological drift into a single vast supercontinent. Geologists call it Pangaea. The name comes from ancient Greek and means simply all earth, not as a metaphor, not as poetic flourish, but as a literal description. It was all the earth, every piece of it fused into one enormous landmass that stretched from pole to pole and from one edge of the world to the other. Stand somewhere in the middle of Pangaea and you could, in theory, walk for months in any direction and still not reach the sea. From what would one day become the frozen continent of Antarctica, north through what would eventually be South America and Africa, east through what would become Europe and Asia, all of it was connected. One unbroken piece of land, vast and ancient and largely merciless toward anything that tried to live too far from water. The interior of this supercontinent was a place of almost incomprehensible dryness. Here is why. When air moves across an ocean, it absorbs moisture through evaporation. It becomes heavy with water vapor, and as it travels inland and cools or rises over terrain, it releases that moisture as rain. But there is a limit to how far that moisture can travel before it has been exhausted. The farther from the coast you go, the drier the air becomes. On modern continents, this effect is familiar. Coastal regions tend to be wetter. Interiors dry out. Central Asia is drier than coastal China. Nevada is drier than California. Australia's interior is one of the driest places on Earth. On Pangaea, this effect was amplified to a degree that had almost no parallel in the history of the planet. Because Pangaea was so enormous, because its heart was so far from any ocean in every direction. The air that reached the interior of the supercontinent arrived stripped almost completely of moisture. There were no inland seas large enough to supplement what the ocean winds could not deliver. There were no mountain ranges positioned in a way that would force moist air upward and squeeze rain from it before it dissipated. The result was a vast, hot, oxidized desert that covered the heartland of the supercontinent for thousands of miles in every direction. If you had been transported to the middle of Pangaea 250 million years ago, you would have seen something that felt more like the surface of Mars than anything resembling the green and varied world we know. Flat red rock stretching to the horizon in every direction. Gravel plains polished smooth by the wind. Low ridges of ancient stone worn to gentle curves by millions of years of erosion. The sky above a hard, merciless blue with no clouds softening it. Temperatures in the day that could climb to levels incompatible with most complex life as we understand it. At night, the thin, dry air holding no warmth, the temperature plunging rapidly, the stars above so numerous and so brilliant in that clean, unpolluted atmosphere that they would seem unreal to modern eyes. Nothing moved in that interior, nothing could live there. Life existed, but it existed on the margins. Along the coastlines of Pangaea, where ocean moisture could reach the land, there were forests. Strange forests. Unlike anything you would recognize from the world today. No flowering plants grew anywhere on Earth at this time. No grass softened any slope or riverbank. The plant life was dominated by seed ferns, tall tree-like plants with feathery fronds spreading from their crowns, by primitive conifers carrying their seeds in dense woody cones, by cycads standing in stiff geometric rosettes, by giant horsetails growing in dense thickets along every waterway. These were the forests of the Permian and early Triassic, and they clung to the edges of the great red interior like a green hem sewn along the margins of a vast and empty garment. And within those forests, and on the coastal floodplains, and in the muddy estuaries where rivers met the sea, life went on. But it was life in recovery. Because the world 250 million years ago was still recovering from something almost unimaginable. Just a few million years before this point in time, the Earth had experienced the worst mass extinction in the entire history of complex life. The event is known formally as the Permian-Triassic extinction event, though it is sometimes called simply the Great Dying, and that name is not an exaggeration. Roughly 96% of all marine species had gone extinct. Around 70% of all land-dwelling vertebrate species had disappeared. Entire lineages of animals that had evolved and diversified and filled the oceans and the landscapes over hundreds of millions of years were simply gone, erased from the living world in what amounted geologically to an eye blink. The cause was volcanism on a staggering scale. A volcanic system centered in what is now Siberia had been erupting in enormous flood basalt events for roughly 2 million years, pumping carbon dioxide and sulfur dioxide and other toxic gases into the atmosphere at rates the planet had rarely, if ever, experienced. Temperatures rose, the oceans acidified, oxygen levels in the deep sea collapsed, food webs unraveled from the bottom up. The world went through a cascade of failures so severe that life itself came within reach of something like complete collapse. The total biomass of Earth, the combined weight of all living things, may have declined by 90% or more during the worst of it. By 250 million years ago, the most violent phase of those Siberian eruptions had quieted. The killing had slowed, but the world they left behind was simplified and strange. The complex ecosystems of the late Permian period, those intricate, beautifully woven networks of life built over hundreds of millions of years of careful evolution, were largely gone. What remained were the survivors, the tough ones, the generalists, the ones that had managed to find some small refuge from the dying and hold on through sheer biological stubbornness until the worst was over. Among the dominant land animals of this early Triassic recovery period were creatures called synapsids. You may not have heard that name. Synapsids do not have the fame of the dinosaurs, and they do not have the cultural presence of the great prehistoric animals that populate our books and museums and imaginations. But they were remarkable creatures, and they are, in a very direct sense, more relevant to your existence than you might expect. Synapsids were the branch of the vertebrate family tree that would eventually produce the mammals. They had been the dominant land animals of the late Permian, the rulers before the Great Dying reduced them so catastrophically. Even after losing nearly everything in the extinction, a few synapsid lineages had survived, and in the early Triassic they were beginning, slowly, to rebuild. Picture them. Some were large, heavy herbivores, broad and low-slung with barrel bodies and wide skulls, moving slowly across the muddy coastal floodplains and browsing on the recovering vegetation with a patient, unhurried thoroughness. Some were predators, with deep jaws and teeth that showed the very earliest stages of the differentiation that would one day characterize mammal dentition, different teeth for different jobs, incisors at the front for gripping, canines at the corners for killing, grinding surfaces further back for processing food. The cynodonts among them were the most advanced, some showing evidence of whisker pits that suggest sensory facial hair, some with upright posture that was beginning to approach the efficiency of mammal locomotion, some possibly already experimenting with insulating body coverings, not entirely unlike fur. These animals were not yet mammals, they were something else, something in between, but they were moving in that direction, step by slow evolutionary step, and they were the largest and most ecologically significant land animals of the early Triassic world. Alongside the surviving synapsids, the archosaurs were also beginning their own recovery and radiation. Archosaur is a technical term, but the concept it describes is straightforward. This was a group of reptiles that diverged from a common ancestor in the early Triassic and began moving in several distinct evolutionary directions at once. One archosaur lineage eventually gave rise to the crocodilians, the ancestors of the modern crocodile and alligator and their relatives. A different archosaur lineage gave rise to the pterosaurs, the remarkable flying reptiles that would eventually share the Jurassic skies with the first birds. And one particular archosaur lineage, the one that would matter most to our story, eventually gave rise to the dinosaurs. But in the early and middle Triassic, the dinosaur lineage was tiny, marginal, almost invisible against the larger backdrop of archosaur life. The archosaurs that actually dominated the middle Triassic landscape were not dinosaurs at all. They were creatures called Relaxatians, and they were formidable in a way that deserves to be described carefully. Picture a Relaxatian. Imagine an animal built somewhat along the lines of a large crocodile, but with modifications that made it significantly more capable on land. Where a modern crocodile sprawls, its legs out to the sides and its belly close to the ground, many Relaxatians had legs positioned more directly beneath their bodies, giving them a more upright and powerful stance. Some Relaxatians grew to enormous size, with skulls 3 feet long packed with serrated teeth designed for cutting through flesh and bone. Postosuchus is among the best known, reaching perhaps 15 feet in length, moving with a slow and stalking authority through the fern-lined riverbanks and open coastal forests of middle Triassic Pangaea. These were the apex predators of the Triassic, and they were everywhere. Alongside the predatory Relaxatians were the etosaurs, armoured herbivores that occupied an ecological role roughly analogous to that of large armoured mammals in the modern world. They walked on 4 stout legs, their bodies covered in rows of interlocking bony plates that provided protection against the teeth and claws of the predators that shared their world. Some etosaurs reached lengths of 15 feet or more. They were common and widespread, their fossils turning up in Triassic deposits across North America, Europe and South America. Then there were the rhynchosaurs, chunky, 4-legged herbivores with distinctive beaked mouths, specialized for processing the tough seed ferns and other coarse vegetation that made up so much of the Triassic plant world. Rhynchosaurs were, in some ecosystems, the most numerically common large animals present. Their fossils occur in extraordinary numbers at certain sites, suggesting that they moved in large groups, foraging across the coastal plains and forest margins in the way that large herd animals dominate certain modern grasslands. This was the world of the Middle Triassic, perhaps 235 million years ago. A world of survivors rebuilding themselves into new configurations, a world of fern forests and cycad groves and the vast empty red interior. A world presided over by the Relaxatians and their archosaur relatives, by the recovering synapsids, by all the strange and wonderful animals that evolution had produced in the aftermath of the Great Dying. And somewhere in this world, moving quietly through the underbrush, keeping to the shadows and the margins, avoiding the great predators and living off small prey and opportunistic scavenging, were the earliest dinosaurs. They were not impressive. The very first animals we would recognize as belonging to the dinosaur lineage were small, Most estimates suggest the earliest forms were no longer than 3 to 5 feet, from snout to tip of tail. They were bipedal, moving on 2 legs while holding their forelimbs off the ground, which gave them a distinctive upright posture and freed their hands for grasping. Their necks were relatively long, their heads were small and lightly built, their teeth were simple, suited for catching insects and small lizards, and perhaps the occasional egg when a nest was left unguarded. Their legs were long and slender beneath their bodies, giving them a speed advantage over the sprawling belly close to the ground locomotion of most other reptiles. But they were not dominant. They were not successful in any meaningful sense by the standards of the time. The earliest known dinosaurs, forms like Nyasasaurus from what is now Tanzania, and the slightly later Eoraptor and Herrerasaurus from the Ashigualasto formation of what is now Argentina, were background creatures, bit players in a world that barely noticed them. If you had stood in a middle Triassic landscape and tried to identify, from the animals moving around you, which group would one day inherit and rule the entire terrestrial world for 165 million years, you almost certainly would have pointed to the Rauisuchians, or possibly the Synapsids. You would have walked right past the small, quick, bipedal thing rustling through the undergrowth without giving it a second glance. It was small, it was quick. It lived in the margins where the dominant animals did not bother to look. And yet something was different about it. Something not yet fully expressed, not yet fully revealed. Something that was waiting, with the patience that evolution always has, for the world to change in its direction. That something was the beginning of the longest reign in the history of land life. And the world was about to change. Deep beneath the crust of Pangaea, in volcanic provinces that had been building pressure for tens of millions of years, enormous forces were beginning to move. The climate that had kept the Rauisuchians in power, and the rhynchosaurs in their millions, and the seed ferns in their coastal forests, was about to be pushed beyond the limits of its stability. The first drops of something unprecedented were just beginning to fall. There is a particular quality to the air in the moments before a very large storm. You may have felt it at some point in your life. The wind stops, the birds go quiet, the temperature drops by 1 or 2 degrees in the span of a single breath. The quality of the light changes, turning the world briefly into something slightly strange and beautiful, every colour slightly more saturated than usual, every shadow slightly deeper. The whole landscape seems to pause, to hold itself in a kind of suspended waiting. Everything is still and expectant. Now imagine that stillness, that moment of atmospheric tension before the sky opens, stretched across thousands of years. The world of the mid-Triassic had been stable in its extreme way for a long time. The same patterns, year after year. The same coastal monsoons drenching the narrow green margins of Pangaea's edges. The same bone-dry continental interior baking under the sun. The same Rauisuchians stalking the riverbanks. The same rhynchosaurs grazing the fern meadows. The same small dinosaurs moving through the underbrush, marginalized and unremarkable. And then, around 234 million years ago, something began to change. It started almost imperceptibly. A monsoon season slightly longer than usual in certain coastal regions. Rain falling for a few extra weeks before it finally relented and the dry season arrived. Rivers remaining slightly higher through the dry period. Soils retaining moisture a little deeper, a little longer. Nothing dramatic. Nothing that would have alarmed even the most observant creature living through it. But the change did not stop. It grew. The next season, the rains were heavier. The rivers spread wider across their floodplains. New ponds appeared in depressions that had been dry for years. The dry season, when it came, was shorter than before and less complete, leaving the ground damp rather than truly desiccated. The season after that, the rains came earlier. They were heavier still. They lasted longer. They reached farther into the continental interior than they had in living memory, or in any memory encoded in the genetics and behaviour of the animals that endured them. The landscape was beginning to change. Not dramatically, not all at once, but steadily, persistently, with a direction and a momentum that would, over thousands of years, and then hundreds of thousands, and then millions of years, transform the entire surface of the planet. Scientists call what followed the Carnian pluvial episode. The name is precise but understated. Carnian refers to the specific stage of the Triassic period during which this occurred. Pluvial means simply of or relating to rain. So in plain language, This was the Carnian rainy time, 2 million years of dramatically elevated rainfall across the entire globe. A climate event so extreme and so prolonged that it fundamentally restructured every terrestrial and many marine ecosystems on Earth. The cause was volcanism, as so many of Earth's greatest transformations have been. Deep within the planet, beneath what is now the Pacific Northwest of North America, a vast volcanic province called the Wrangellia, large igneous province, had been building. This was not the kind of volcano most people imagine when they hear the word. Not a single tall cone erupting in a dramatic column of ash and steam that eventually quiets and cools. This was something much larger and much stranger, a flood basalt eruption. In a flood basalt event, magma does not concentrate in a central vent. Instead, it finds its way to the surface through enormous fissures in the Earth's crust, great gaping cracks that can extend for hundreds of miles. The lava that pours from these fissures does not pile up into mountains. It spreads outward in vast flat sheets, flowing across the landscape and covering everything in its path with layer upon layer of dark, heavy rock. The Wrangellia eruptions eventually produce something between 1 and 3 million cubic kilometers of lava. If you tried to picture that quantity, imagine burying the entire continental United States under 100 meters of solid rock. That is roughly the volume of material that erupted not all at once, but in pulses and waves spread over hundreds of thousands of years. And with every eruption, with every new pulse of magma finding its way to the surface, came gases. Carbon dioxide, sulfur dioxide, water vapor, methane, hydrogen, sulfide. These volcanic gases were released into the atmosphere in quantities that make anything in human industrial experience look trivial. Each major eruption phase likely emitted more carbon dioxide in a geologically brief period than all of human civilization has produced across its entire history. And the eruptions continued, on and off, in pulses separated by periods of relative quiet, for roughly 2 million years. Carbon dioxide in the atmosphere is a greenhouse gas. It traps heat from the sun, preventing it from radiating back out into space. As atmospheric carbon dioxide levels rose, global temperatures began to climb, slowly at first, then faster. The feedback mechanisms activated one by one. Warmer temperatures cause more evaporation from the oceans. More evaporation puts more water vapor into the atmosphere. Water vapor is itself a greenhouse gas, so more water vapor means more warming. More warming means more evaporation. The system spirals. The hydrological cycle, the great planetary engine that moves water from the oceans into the atmosphere and back to the surface as precipitation, began to accelerate in ways the world had not experienced in a very long time. The oceans of the Triassic world were vast. Pangaea, for all its enormous size, covered only about 1/3 of Earth's surface. The remaining 2/3 were covered by a single, world-spanning ocean called the Panthalassic Ocean, the largest single body of water in Earth's history, stretching from pole to pole, broken only by the great landmass of the supercontinent. As global temperatures rose, the surface waters of this immense ocean began to warm. Warm water evaporates faster than cold water. The equatorial regions of the Panthalassic became enormous engines of evaporation, pumping water vapor into the atmosphere at rates unprecedented in the living world's recent experience. That vapor rose, it was carried inland on the wind, and it came back down. The monsoon systems that had always brought seasonal rain to the margins of Pangaea began to intensify. Not gradually and moderately, but dramatically and catastrophically. The seasonal storms that had been powerful but bounded became something else entirely, something for which we barely have adequate language because nothing in the modern world resembles it closely enough to serve as a comparison. These were continental-scale weather systems, atmospheric circulation patterns, driven by temperature differentials so extreme they generated rain events that would have been described by any living observer as something between a storm and the end of the world. Imagine standing on what would one day become Central Europe during the peak of the monsoon season at the height of the Carnian pluvial episode. The sky above you is not blue. It has not been blue for weeks. It is a dense, heavy, oppressive grey, a ceiling of clouds so low and so thick that it seems to press down on the tops of the tallest trees, absorbing the forest into itself. The air is extraordinary, not merely humid in the way a warm summer morning might be humid, but genuinely thick, almost liquid in quality, so saturated with moisture that each breath you draw, feels slightly more like drinking than breathing. The warmth is immense and pervasive, a heat that comes not from direct sunlight, which you have not seen in a long time, but from the atmosphere itself, from all that accumulated moisture holding its warmth against the surface of the earth. And then the rain begins. Not a shower, not even a thunderstorm in the sense you might understand that word. What descends is a curtain of water so dense that visibility drops to a few feet within seconds of it starting. The sound is total, an absolute roar that fills your skull and makes thought difficult. The individual drops striking leaf and stone and water so rapidly they blur into a single continuous roar. The ground disappears under an inch of running water within minutes, then 2 inches, then 6. The water is warm and dark with suspended sediment, and it is moving, finding the low points in the landscape and flowing there with an urgency that quickly becomes alarming. This rain does not pause in an hour, it does not stop in a day. It rains for a week without meaningful interruption, then 2 weeks, the rivers that had been modest seasonal waterways swelling to enormous and powerful floods, spreading out across floodplains that had been red and dry and cracked for thousands of years. When the rain finally lightens, after weeks or months of this sustained deluge, it does not stop entirely. It merely reduces to a steady, persistent fall that continues day after day after day, maintaining the new water table, filling every depression in the landscape, keeping every valley floor wet and soft. And this went on, in pulses and waves and long sustained periods for 2 million years. Scientists can read this history with extraordinary clarity in the rocks themselves. When geologists study Triassic period rock formations, they encounter a very specific and consistent pattern in deposits laid down during the Carnian stage. Beneath the Carnian layers, the rock is red. These are oxidized sediments, the kind that form in hot, dry conditions where iron in the soil is exposed to oxygen and turns the characteristic rusty red. Red rock means dry world. Dry world means stable arid conditions. Stable arid conditions means the familiar Triassic landscape of coastal forests and vast empty interior. Then the rock changes colour. Suddenly and distinctly the red gives way to grey. These are water-deposited sediments, the kind that form in rivers and lakes and swamps and marshes. Grey rock means wet world, and these grey layers are thick, not a thin stripe of unusual deposition. Hundreds of metres of grey sediment, representing millions of years of persistent, intense rainfall. The same pattern, red below then grey, appears in Triassic rock formations across every continent: Italy and Austria and Germany, Britain and Poland, Argentina and Brazil, China and Australia, Antarctica, which was still ice-free and positioned much farther north than its modern location. Everywhere that has Triassic rock, the same sequence appears at the same point in geological time. This was a global event. Something had happened to the entire climate system of the planet simultaneously. And the fossils preserved within those grey Carnian layers tell a story of profound and sometimes catastrophic transformation. The seed ferns that had dominated the plant communities of Pangaea began to disappear. Dicroidium, a distinctive seed fern whose pollen and fossilized leaves appear in enormous quantities in pre-Carnian deposits, began its long decline during the wet period. Its root systems, evolved over millions of years to penetrate deep into dry soil in search of water during long dry seasons, could not function in permanently saturated ground. Waterlogged soil is physiologically suffocating for plants adapted to drought. Root rot set in. Fungal pathogens that the periodic dry seasons had previously kept in check exploded in the constant humidity and attacked the seed fern communities with devastating effectiveness. Breeding cycles that depended on the rhythms of wet and dry seasons lost their environmental cues and stopped working properly. Within a few 100,000 years of the Carnian pluvial episode reaching its full intensity, forests that had stood and thrived for tens of millions of years were collapsing. The animals were following the plants into difficulty. The Rauisuchians, the great predatory archosaurs that had presided over the Triassic landscape with such evident authority, were among the first large animal groups to suffer. Their enormous bodies required enormous territories. Those territories were flooding. Their preferred nesting locations, dry sandy areas where they buried their eggs and waited for the sun-warmed ground to incubate them, were underwater. The prey species they had evolved to hunt were declining or disappearing. The sheer energetic cost of moving a massive body through permanently waterlogged terrain was a drain their metabolisms could not easily absorb. The etosaurs lost their food as the seed fern communities collapsed around them. The rhynchosaurs, those ubiquitous pig-like grazers, vanished from the fossil record with striking speed as the vegetation they depended on disappeared. Some researchers believe the rhynchosaurs were among the fastest large vertebrate disappearances of the entire Triassic period. Their decline so rapid that the transition from common to absent spans only a relatively thin layer of rock. Niche after niche emptied. Ecosystem after ecosystem across the face of Pangaea lost its dominant species and sat waiting, like a furnished room from which all the residents had departed. And every empty niche was a door. Every extinct species was a space in the world waiting to be filled by something with the flexibility and the adaptability to move in and take it. The dinosaurs were small, they were fast, they were omnivorous generalists in a world where dietary specialists were losing their food. They were upright walkers in a world where the terrain had become difficult for sprawling animals. They were, by some indications, more metabolically active than their competitors in a world where the sun had stopped being reliable. The old world was ending. The rain was dissolving it, washing it away layer by layer, the way persistent water reshapes even the hardest stone. And in the new world forming in its place, the dinosaurs were about to discover that everything that had made them marginal in the old world made them precisely suited for the one that was emerging from the mud and the flooding and the transformed landscapes of the greatest sustained rainfall event in Earth's history. Breathe slowly. The rain is falling all around you, warm and steady and ancient, across a world that is changing with a patience measured in geological time. Let the sound of it carry you. Let the story continue at whatever depth of consciousness feels right to you. The world is changing, and the dinosaurs are ready. There is something quietly moving about watching a small, overlooked thing become great. Not through conquest, not through brute force or sudden dramatic victory, but through the accumulated advantage of small traits that in a stable world mean very little, but in a changed world mean everything. Through the patient compounding of biological advantages that were invisible when the world was settled but became decisive the moment the world destabilized. Through being, by some combination of fortune and preparation, exactly the right shape for the moment that finally arrived. The early dinosaurs were that thing. When the Carnian pluvial episode began reshaping the world around 234 million years ago, the dinosaurs that existed at the time were already present, but they were genuinely minor. Best estimates suggest they made up somewhere around 5% of the animal community in any given ecosystem, possibly less. They were not dominant herbivores. They were not apex predators. They were quick, bipedal opportunists living on small prey, on insects and lizards and eggs and whatever plant material could supplement an inadequate diet. They stayed out of the paths of the large predators that ruled their world. They lived quietly and mostly unnoticed in the underbrush. But they had something, a collection of quiet advantages that the world had not yet found a use for. The first and most fundamental of these advantages was their posture. Consider how most reptiles of the Triassic moved. A Rauisuchian, sprawling somewhat like a modern crocodile, held its legs out to the sides of its body. Its belly was relatively close to the ground. With every step, its body swayed from side to side, the muscles of its torso working to stabilize against the lateral momentum of its own weight. This sprawling gait was not inefficient exactly. Crocodilians today are capable of surprising speed over short distances, and the Rauisuchians were certainly effective predators. But the sprawling gait had a cost, an energetic overhead, a tax paid with every single step. Dinosaurs were different in a way that proved foundational. Their legs were positioned directly beneath their bodies, oriented vertically like pillars supporting a structure. This erect posture, which paleontologists call a parasagittal stance, allowed dinosaurs to move with substantially greater energy efficiency than their sprawling contemporaries. Each step drove the animal forward without the sideways sway, without the lateral stabilization tax. The muscles doing the work were primarily those driving the limb forward and backward, not spending energy fighting against the natural tendency of a wide-based sprawling body to tip from side to side with every footfall. Over the course of a long day of foraging and hunting and fleeing and exploring, this efficiency advantage compounded significantly. an animal that spends 10% less energy per step than its competitor can, over the course of a day, cover more ground, catch more prey, or simply arrive at the end of the day with more energy reserves than the sprawler beside it. These are the kinds of margins that evolution works with. Small advantages, reliably expressed generation after generation. In the wet, waterlogged world being created by the Carnian pluvial episode, this efficiency advantage became even more significant. Moving through mud and shallow water is energetically expensive. Sprawling animals with their legs out to the sides tend to sink deeper into soft substrate with every step, their wide footprint area and low body height working against them in saturated ground. An upright animal with legs positioned under its body can pick its feet up more cleanly, take longer strides, keep its body higher above the waterlogged surface. In a landscape that was often ankle-deep or knee-deep in standing water and mud for months at a time, being able to move efficiently through that terrain without exhausting yourself was not a minor convenience. It was a serious competitive advantage. The second great advantage of the early dinosaurs was almost certainly their respiratory system. Modern birds, the direct living descendants of theropod dinosaurs, possess one of the most sophisticated breathing systems in the animal kingdom. Rather than simply filling a pair of lungs and then emptying them with each breath cycle, birds move air through their respiratory system in a largely one-directional flow, passing it through a series of interconnected air sacs distributed throughout the body and even extending into the hollows of bones. This system extracts oxygen far more efficiently from each breath than the tidal breathing of mammals or the simpler lung systems of most reptiles. It is why birds can fly at altitudes and maintain activity levels that would be impossible for animals with less efficient respiratory designs. There is compelling evidence based on the structure of the vertebrae and ribs in many early dinosaurs that at least some dinosaurs had a similar or functionally analogous system of respiratory air sacs. This evidence comes from the same hollow spaces in the bones that we associate with the air sac extensions in living birds. If some early dinosaurs breathed in this way, then they would have been extracting more oxygen per breath, sustaining higher activity levels, and coping with atmospheric disruptions caused by volcanic gases more effectively than their competitors. In the cloudy, rain-soaked, volcanically perturbed atmosphere of the Carnian pluvial episode, that efficiency would have been an extraordinary advantage. The third potential advantage was metabolic, and it is the one that remains most contested among paleontologists. The question is simply this: were the early dinosaurs warm-blooded or cold-blooded? Did they regulate their own body temperature internally, or did they rely on external heat sources the way modern lizards and crocodiles do? The answer, from the available evidence, is almost certainly somewhere in between, and varies across different dinosaur lineages. The growth rings preserved in dinosaur bone, or more precisely the absence of growth rings in many dinosaur bones, suggest that many dinosaurs grew continuously throughout the year rather than in the seasonal bursts and pauses typical of cold-blooded animals. Their bone microstructure in many cases resembles that of fast-growing metabolically active animals more than that of slow, cold-blooded ones. Whether or not the earliest dinosaurs were fully endothermic, any tendency toward higher metabolic activity and more consistent internal temperature regulation would have been enormously useful in the Carnian pluvial episode's wet, cloudy world. Cold-blooded animals depend on sunlight to warm their muscles and keep themselves active. When the cloud cover is persistent, when the sun disappears for weeks at a time behind the thick grey ceiling of a Carnian mega-monsoon, cold-blooded predators become sluggish and slow. An animal that can stay active regardless of whether the sun is shining, one that generates its own warmth from within, is a consistently effective hunter, in conditions where its sprawling competitors are sitting still, waiting for warmth that may not come for days. These advantages, the upright posture, the efficient respiration, the metabolic activity, had all been present in the early dinosaurs before the Carnian pluvial episode began. But in the world of the mid-Triassic, with its established dominance hierarchies and its well-occupied niches, these advantages had not been enough to push the dinosaurs out of the margins. The Rauisuchians were too numerous, too established, too thoroughly adapted to the world as it was for the dinosaurs to displace them through competition alone. What the Carnian pluvial episode did was remove that constraint. It did not make the dinosaurs stronger, it made the Rauisuchians weaker. It disrupted the ecosystem that the Rauisuchians had mastered, changed the rules, so that their particular mastery was no longer sufficient, and in doing so, it created the space that the dinosaurs, with their quiet cluster of adaptive advantages, were perfectly positioned to fill. The fossil record reflects this transformation with remarkable clarity. In rock layers from just before the Carnian pluvial episode, dinosaur fossils are rare and fragmentary. A few bones here, some teeth there, a set of small bipedal footprints preserved in ancient mud. The dinosaurs existed, but they were uncommon. Their presence registered only faintly in the geological archive. In rock layers from during and immediately after the main pulses of the Carnian pluvial episode, something changes. Dinosaur fossils become more numerous. New species appear. Body sizes begin to diversify. Some lineages are getting larger, moving into the predator niches that the declining Rauisuchians can no longer defend. Others are experimenting with herbivory, developing new dental adaptations for processing the new vegetation that is spreading across the transformed landscape. Within a few million years, which is very fast in evolutionary terms, the dinosaurs have gone from minor background players to a significant and growing presence in every major terrestrial ecosystem on the planet. Among the early dinosaurs whose fossils illuminate this period, Eoraptor is one of the most informative. Eoraptor lived in what is now Argentina, in the Ischigualasto Formation, in rocks dated to approximately 231 million years ago. It was small, reaching about 3 to 4 feet in length, and weighing perhaps 15 to 20 pounds. It moved on 2 legs, held its long neck and small head at a horizontal angle when walking, and used its grasping 3-fingered hands to seize prey. Its teeth were mixed, with leaf-shaped teeth at the front suitable for processing plant material, and more blade-like teeth further back more appropriate for flesh. This combination suggests an omnivore in the truest sense, willing and able to eat almost anything available, which was precisely the right strategy for a world in which the food web was being restructured almost continuously. Herrerasaurus from the same formation was larger and more committed to carnivory. Reaching perhaps 15 to 20 feet in length, it was one of the bigger early dinosaurs, and its teeth were fully adapted to a meat-eating diet. Its lower jaw had a flexible joint that allowed extra grip on struggling prey, a feature that would be refined and passed down through millions of years of theropod evolution. These animals were the foundation, the first chapters of a story that would run for 165 million years. Colophysys, from the late Triassic of what is now New Mexico, is one of the best known of the early dinosaurs because its fossils have been found in extraordinary numbers. At a site called Ghost Ranch, paleontologists have recovered hundreds or thousands of Colophysys individuals, apparently all killed together in a single event, likely a flash flood that overwhelmed a gathering of these animals before they could escape. That mass mortality site tells us several important things. It tells us that Colophysys were common enough to gather in large numbers. It suggests they may have been social or at least gregarious, moving together through the landscape. And it tells us that they were present in large populations across what is now the American Southwest by the late Triassic, which means their lineage had expanded substantially from the scattered rare individuals of the earlier period. Colophysys itself was slender and fast, about 10 feet long but lightly built, with hollow bones that reduced its weight and enhanced its speed. Its long legs gave it a running stride that would have been difficult for slower, heavier animals to escape. It almost certainly hunted small prey, lizards and small synapsids and large insects, and probably competed with others of its kind for the best territories and food sources. There is something deeply touching about imagining these early dinosaurs moving through the changed Triassic landscape. The world around them was still wet, still transformed, still full of the evidence of the great rains that had restructured everything. New conifer forests were spreading into regions that had been desert for millions of years. New river systems carved channels through ancient red rock. New lakes glittered across what had been parched floodplains. The old dominant animals were gone or going, their places taken by the new. And through all of this, the dinosaurs were walking, quietly, persistently, opportunistically, not yet great, not yet dominant, but walking in the right direction, with the right bodies, at the right time in the history of the world. Plateosaurus appeared in this period and represents one of the most significant early steps in dinosaur diversification. It was a prosauropod, a member of the lineage that would eventually give rise to the enormous long-necked sauropods of the Jurassic. Plateosaurus itself was not enormous by later standards. It reached perhaps 20 to 30 feet in length, moved primarily on 2 legs but could drop to 4 when browsing low vegetation, and had a long neck that allowed it to reach food sources unavailable to shorter-necked competitors. Its teeth were leaf-shaped and serrated, suited for processing plant material. Plateosaurus fossils are found across what is now Germany, France, and Switzerland, often in concentrations that suggest seasonal gatherings, perhaps animals moving together to feeding grounds during the wet season. There is something in those concentrations that hints at the complex social lives these animals may have had, lives that have left very little direct evidence, but that we can infer from the bones accumulating together in the same places, season after season, generation after generation. The diversification of the dinosaurs during and after the Carnian pluvial episode was the opening of a story whose full scope would not become clear for another 50 million years. At this early stage, the dinosaurs were still modest animals in a world that was still recovering and restructuring. They were not yet the giants of the Jurassic or the spectacular diversity of the Cretaceous. They were beginners, experimenting, exploring, expanding, generation by generation filling the spaces that the rain had made available. But the direction was set, the advantages were present. The world had given them its most extraordinary gift, not resources or territory exactly, but something more fundamental. It had given them time and space, room to become what they were capable of becoming. Room to become, in the fullness of geological time, the rulers of the earth. Rest now. Let the images drift past you slowly, the small, quick dinosaurs moving through the wet, transformed forest. The new rivers catching light as they flow through landscapes that have never held water before. The sky beginning, very slowly, after millions of years, to clear. Sleep if you're ready. The story will carry you gently forward. The Triassic world did not end quietly. Very few things in the deep history of our planet do. The great transitions between geological periods are almost always marked by catastrophe, by upheavals that shake the existing order so thoroughly that what existed before becomes unrecognizable in what survives after. The end of the Triassic period, roughly 201 million years ago, was no exception. It was, in fact, one of the more severe mass extinction events in Earth's history, and the dinosaurs lived through it. That they lived through it was not inevitable. By the end of the Triassic period, the dinosaurs had already accomplished something impressive. They had survived the Carnian pluvial episode and had emerged from those 2 million years of climate transformation as a more diverse and ecologically significant group than they had been before. They were no longer purely marginal. They were present in increasing numbers across Triassic ecosystems, filling niches that the declining Rauisuchians and Etosaurs had vacated. Some lineages were getting larger, some were becoming committed herbivores, some were establishing themselves as significant predators. But the world had another test waiting for them. Beneath the surface of Pangaea, in the Great Rift Zone where the supercontinent had been slowly beginning to crack apart, geological forces of enormous consequence were accelerating. The region that would eventually become the Central Atlantic Ocean was a growing zone of crustal extension, where the tectonic plates carrying what would be North America and Africa were slowly being pulled apart, creating a narrow rift that would, over the coming millions of years, grow into an ocean. Along the margins of this rift, and in related volcanic provinces spread across a vast area encompassing parts of what would become North America, South America, Europe and Africa, enormous quantities of magma were finding pathways to the surface. The Central Atlantic Magmatic Province, abbreviated CAMP by geologists who work with it, was one of the largest flood basalt volcanic events in Earth's history. Over a geologically brief period, perhaps 1 million years or less, these eruptions produced millions of cubic kilometers of basalt and injected vast quantities of volcanic gases into the atmosphere. The greenhouse warming that followed was rapid and intense. Global temperatures rose significantly. Ocean temperatures climbed. The chemistry of seawater changed as it absorbed excess carbon dioxide and became more acidic. The same cascade of effects that had driven the Carnian pluvial episode earlier in the Triassic was triggered again, but in a different form and with different consequences. This time the most severe effects were felt in the oceans. Marine ecosystems collapsed on a scale not seen since the Permian-Triassic extinction. The conodonts, tiny eel-like creatures, whose tiny tooth-like phosphatic elements are one of the most common microfossils in the entire Paleozoic and early Mesozoic rock record, went completely and finally extinct. They had survived the Great Dying, they had survived the Carnian pluvial episode, they had been part of the ocean world for hundreds of millions of years. The end-Triassic extinction ended them. Many marine reptile groups were severely reduced. The platosaurs and nothosaurs, the great marine hunters of the Triassic seas, largely disappeared. Reef-building organisms that had been slowly recovering from the Permian destruction were devastated again. Ammonite diversity, which had been building back through the Triassic, crashed to a tiny surviving remnant. On land, the losses were equally severe. The Rauisuchians, the powerful predatory archosaurs that had already been weakened by the Carnian pluvial episode, did not survive the end-Triassic extinction. They disappeared entirely and permanently, leaving the large terrestrial predator niche completely vacant. The etosaurs went extinct. The phytosaurs, a group of crocodile-like predatory archosaurs that had been among the most successful reptiles of the Triassic, vanished from the fossil record. The surviving synapsid lineages were further reduced, squeezed into ever smaller and more marginal ecological roles. Even among the dinosaurs themselves, the end-Triassic extinction was not trivial. Many lineages that had been diversifying during and after the Carnian pluvial episode disappeared. Entire branches of the early dinosaur family tree were pruned away. The diversity that had been building for tens of millions of years was, in substantial part, erased. But the core branches of the dinosaur family survived. This is the remarkable thing, the thing worth pausing to appreciate. While almost everything else that had been competing with the dinosaurs for ecological space during the Triassic was eliminated or reduced to tiny remnant populations, the fundamental dinosaur lineages came through. The theropod branch survived. The sauropodomorph branch survived. The early ornithischians survived. The basic architecture of the dinosaur family tree remained standing when the extinction had done its work. Why? This is a question that paleontologists continue to examine and debate, and there is no single clean answer. But the convergence of evidence suggests several contributing factors. The dietary flexibility that had served the early dinosaurs so well during the Carnian pluvial episode was still present and still valuable. When food webs collapsed during the end-Triassic extinction, species with narrow dietary requirements were more severely affected than generalists. A dinosaur that could eat insects, fruit, seeds, small animals, and plant material had more options available during a period of ecosystem disruption than an animal that had specialized in one particular prey type or one particular plant species. The respiratory efficiency that the air sac system provided may have helped dinosaurs cope with periods of atmospheric disruption. When volcanic gases altered the chemical composition of the air, even temporarily, animals breathing more efficiently from each breath would have had an advantage. And crucially, the end-Triassic extinction eliminated, in one catastrophic stroke, nearly all of the remaining large animal competitors that the dinosaurs had not yet been able to displace. The Rauisuchians were gone, the etosaurs were gone, the phytosaurs were gone, the large synapsids that had been the dominant large herbivores and omnivores of the Triassic were reduced to small, secretive, primarily nocturnal creatures. The playing field was, for the first time in the history of the dinosaur lineage, essentially clear. Imagine the world of the earliest Jurassic period, immediately after the end-Triassic extinction had done its work. The landscapes were altered, the climate had shifted, the volcanic warmth gradually beginning to ease as the camp eruptions slowed. The forests were different, many of the Triassic plant communities replaced by new assemblages better suited to the changed conditions. The air may still have carried traces of the volcanic disruption on certain days, a faint chemical quality to the humidity, a haze on the distant horizon during the wet season. Moving through these emptied and transformed landscapes, crossing the floodplains and threading through the recovering forests and following the river systems that had been reshaped by the latest chapter of climate disruption, were the dinosaurs. They were not yet large, most of them. The lineages that would produce the giants of the Jurassic were still represented by relatively modest animals, long-necked and somewhat bulky, but nothing approaching the scale they would eventually achieve. The predatory theropods were fast and capable, but not enormous. The early ornithischians were small, scattered, experimenting. But there was nothing left to stop them. The ecological space was there, vast and largely empty, waiting to be filled. The resources were there, the recovering forest generating more plant biomass than the surviving herbivores could consume. The niches were there, large predator niches and large herbivore niches and mid-sized predator niches and browser niches and grazer niches and everything else that makes up the full complex architecture of a terrestrial ecosystem. Almost all of them vacant, almost all of them available. The dinosaurs had passed their first great test, not by being the strongest or the most powerful or the most spectacularly adapted predators of their age, by being resilient, by being flexible enough to survive catastrophes that eliminated more specialized, more established competitors, by having the right combination of traits to endure conditions that killed the competition. Two consecutive great extinction events, the Carnian pluvial episode and the end Triassic mass extinction, had, together, cleared the path that the dinosaurs needed. And now that path stretched out before them, open and vast, into 200 million years of open world. They were about to walk it. Let the sound of the early Jurassic forest settle around you in the darkness, the air cool and clean after the last volcanic disruption, the trees recovering, their canopies slowly rebuilding, the rivers running clear and steady between their banks, and the footprints in the soft mud beside those rivers, small at first, bipedal, precise, belonging to animals that are no longer background creatures. They are the main characters now, and the world they are about to inherit is extraordinary. Close your eyes and picture the most beautiful forest you have ever seen. Now make it larger. Make every tree twice as tall, their trunks rising from deep soft humus that has been accumulating for centuries, their crowns spreading wide and dense overhead. Make the canopy so complete that when you look straight up through the layers of leaf and branch above you, you cannot see the sky at all, only receding levels of green and shadow, and the diffused golden-green light that filters down through all that living architecture to reach the forest floor where you're standing. Make the air thick with moisture, and the smell of warm soil and slow-growing things, resin from the conifers, and the rich organic scent of deep mulch, and the clean, slightly sharp smell of standing water in the depressions nearby. Make the sounds layered and continuous, the steady background of insects, the calling of unfamiliar creatures in the canopy, the distant resonant creak of very large trees in the slow wind. And deeper than all of that, occasional and immense, the sounds of very large animals moving somewhere in the middle distance. Now make the largest animals in that forest 60 feet long. Now make them 80. Now make the largest ones, moving slowly and with immense, peaceful, unhurried dignity through the deepest parts of the forest where the trees are tallest and oldest, 100 feet long and weighing 60 tons or more. This is the Jurassic period, and it is one of the most magnificent things this planet has ever produced. The Jurassic spans from roughly 201 million years ago to 145 million years ago. Within those 56 million years, the dinosaurs went from survivors of the end Triassic extinction to the undisputed rulers of every terrestrial environment on the planet. They diversified into more ecological roles than any land animal group before them had occupied. They evolved into body shapes and sizes that stretched the limits of what we might have imagined biology capable of producing. They built ecosystems of extraordinary complexity and remarkable stability. And through all of it, the most iconic, the most awe-inspiring, the most quietly magnificent of them were the sauropods. The sauropods were the long-necked dinosaurs, the giants. Their name means lizard feet, which tells you something about how the earliest scientists to describe them classified them, focusing on the broad columnar legs rather than the far more striking architecture above. But the defining characteristic of sauropods was not their feet. It was the whole extraordinary proportional system of their bodies. The necks, impossibly long, stretching out from the shoulders in a horizontal sweep that could sometimes extend 30, 40, 50 feet. The small heads positioned at the ends of those necks, surprisingly delicate for animals so enormous, equipped with simple peg-like or spoon-shaped teeth designed for stripping vegetation rather than chewing it. The massive barrel-shaped torsos, deep and wide, housing digestive systems immense enough to process the tonnage of plant material these animals needed every day. The long counterbalancing tails, sweeping out behind, keeping the animal's weight distribution stable. the 4 legs planted in the earth with the solidity of pillars, each footfall leaving an impression in the soft Jurassic soil that would persist for millions of years, eventually mineralizing into the trackways that paleontologists now find preserved in rock around the world. Brachiosaurus was one of the most spectacular examples of sauropod design. It lived in what is now North America and possibly East Africa, in deposits dated to approximately 150 million years ago, during the late Jurassic period. Brachiosaurus was unusual among sauropods in a way that immediately catches the eye in skeletal reconstructions or museum displays. Its forelimbs were longer than its hind limbs, which is almost unprecedented among large animals, and gave Brachiosaurus a distinctly giraffe-like silhouette, its shoulders higher than its hips, its entire body tilted slightly forward and upward toward the head. When Brachiosaurus raised its long neck to full height, it could reach vegetation approximately 50 to 60 feet above the ground. No other land animal in Earth's history has been able to browse at that height. Its total body length was approximately 85 feet. Its estimated weight ranged from somewhere between 30 and 60 tons, an enormous range of uncertainty that reflects how difficult it is to reconstruct soft tissue mass from bone alone. But even at the lower end of that estimate, Brachiosaurus was by far the largest animal to walk the land at any point in the history of complex life up to that time. Imagine standing near one. Not dangerously close, not in its path, just somewhere in the open forest, perhaps 150 feet away, in a clearing where the trees thin out and you can actually see the full animal without your view being blocked by trunks and undergrowth. You've been aware of it for a few minutes before you see it clearly, aware of the vibrations in the ground that travel up through your feet, a slow, deep rhythm that does not match the footfall cadence of any familiar animal. Then it steps into your line of sight between 2 ancient conifers, and what you feel first is not the word large or the word big or any category of size that human experience has prepared you for. What you feel is something closer to the sensation of looking at a mountain and realizing it is moving. Its feet are planted with a heaviness that you can feel as much as hear. The ground around each footprint is compressed into shallow concentric ridges by the force of that weight. Its legs are wider than old-growth trees, the skin on them a pale grey with a texture like old, dry hide stretched over something tremendously solid. Its body, when you try to take it all in at once, extends beyond your comfortable field of vision, so that seeing the whole animal requires you to turn your head from one end to the other, and the neck. The neck rises above you like a living tower, curving slightly against the light filtering through the canopy, its skin a different texture from the body, smoother, marked with subtle patterns you cannot quite make out at this distance. The neck sways in a slow, deliberate arc as the head moves from side to side, sweeping through the upper canopy with a patient thoroughness, pulling branch after branch into the small mouth with quiet mechanical efficiency. The sounds this action makes are extraordinary in their own right. The ripping of large branches, the deep, resonant grinding of teeth against tough conifer growth. Every movement is unhurried. There is no urgency about this animal, no hurry. It has more food available than it can possibly consume in a day, and it knows, in whatever wordless way an animal knows things, that the world is generous. Diplodocus was a different expression of sauropod design. Where Brachiosaurus was upright and giraffe-like, built for browsing the high canopy, Diplodocus was horizontal and serpentine, its neck and tail extending in opposite directions from a body that was relatively low to the ground. It was nearly 90 feet long from snout to tail tip, possibly longer, making it one of the longest animals ever to walk the earth, but its height at the shoulder was far more modest than Brachiosaurus. Its neck was long and slender, adapted for sweeping low-growing vegetation with wide lateral movements, rather than reaching into the high canopy. At the other end, its tail tapered to a long, thin, whip-like tip that some researchers believe was capable of producing a supersonic crack when swung rapidly. Imagine a herd of Diplodocus in the late afternoon light of a Jurassic floodplain. Perhaps 15 animals, spread loosely across an area of open ground between stands of tall conifers, their movements unhurried and rhythmic. The ground trembles under the combined weight of their slow progress. Their tails sway with each step, and occasionally one of them sweeps its tail in a sudden wide arc, the crack travelling away across the floodplain and startling birds, if there are birds here yet, from the canopy edge. Their long necks sweep back and forth through the low ferns and the ground cover. Their footprints, each as large as a bathtub, fill slowly with water from the wet season just past, forming a trail of small ponds that smaller animals will drink from in the days after the herd has moved on. There is a deep, almost geological peace about watching them. They are not hurrying. They are not threatened, not by anything in this world. They are simply eating and moving and existing on a scale that seems to belong to a different order of physical reality than the scale on which most other life operates. They are the largest land animals that have ever existed, and they carry that size with a quiet gravity that feels, to the watching mind, more like a geographical feature than an animal characteristic. The predators of the Jurassic were built to match the scale of the world they inhabited, and they deserve their own moment of careful attention. Allosaurus was the dominant large predator of the late Jurassic in what is now North America, and possibly in other parts of the world as well. A theropod dinosaur reaching approximately 35 to 40 feet in length, Allosaurus was built not for sustained speed, but for power and ambush. Its skull was large, deep, and kinetically jointed, meaning the bones of its skull could flex and pivot slightly against each other, allowing Allosaurus to open its mouth to an extraordinary width and to deliver its bite with a mechanism described by some researchers as more like a hatchet than the clamping bite of a modern crocodile. Its teeth were serrated on both edges, curved and blade-like, designed for slicing through flesh and separating large portions of meat from a carcass with each movement. Its arms were shorter than its legs but far from vestigial, powerful limbs ending in three-fingered hands tipped with large curved claws, each as long as a human hand. These claws could grip and hold and tear. They were weapons as much as the jaws were. The hind legs were massive, each footful capable of driving enormous force through the ground, the long foot bones elevated off the ground in what is called digitigrade locomotion, walking on the toes rather than the flat of the foot, a design feature it shared with all the theropods and that gave it both speed and grip on varied terrain. There is fossil evidence of Allosaurus attacking Diplodocus and other large sauropods. Diplodocus tail vertebrae have been found bearing marks consistent with Allosaurus tooth serrations. Allosaurus shoulder bones have been found with what appear to be healed wounds consistent with impacts from large herbivore tails or defensive charges. The relationship between the giant predator and the giant prey was not theoretical. It happened. The bones remember. The Jurassic world was also rich with life at every scale beneath the giants. The stegosaurs were among the most distinctive and recognizable of the Jurassic dinosaurs. Stegosaurus itself, from the late Jurassic of North America, was approximately 17 to 20 feet long and carried two alternating rows of large, diamond-shaped bony plates along its back. These plates, which were not solid bone but had a complex internal vascular structure suggesting high blood flow through them, have been the subject of more than a century of scientific debate regarding their function. They may have served in heat exchange, absorbing or radiating thermal energy. They may have been display structures used in species recognition or mate attraction. They may have been both. What is not debated is the function of the four large bony spikes at the end of its tail, arranged in two pairs. These were weapons, and fossil evidence confirms that they were used. Allosaurus specimens with healed puncture wounds whose dimensions precisely match the Stegosaurus tail spike have been recovered. The two animals were adversaries in the truest sense. Kentrosaurus, a stegosaur from what is now Tanzania, was smaller than Stegosaurus and carried its armour in a more varied arrangement, with both plates and spikes along its back and tail, the spikes extending outward at angles that would have made an attack from behind or the sides extremely hazardous for any predator. In the skies above the Jurassic landscape, the pterosaurs were diversifying rapidly. These were not dinosaurs, technically. They were archosaurs, close relatives of the dinosaur lineage that had taken an entirely different evolutionary path, one leading not to large ground-based animals, but to the first vertebrates to achieve powered, sustained, flapping flight. The earliest pterosaurs appeared during the Triassic, but it was in the Jurassic that they truly flourished. They ranged from small forms perhaps the size of modern sparrows or pigeons, likely hunting insects with quick aerial maneuvers, to animals with wingspans of several feet, soaring on thermals above the Jurassic forests and coastlines. Rhamphorhynchus, from the same German deposits that would later yield Archaeopteryx, was a long-tailed pterosaur with a wingspan of roughly 3 feet and a remarkable array of needle-like teeth in its jaws, almost certainly a fish-eater. Its long tail ended in a diamond-shaped vein that may have served as a rudder during flight, giving it stability and control as it banked and turned above the shallow Jurassic lagoons. Dimorphodon, from the early Jurassic of what is now England, had a remarkably large head for its body size, deep and parrot-like, in sharp contrast to the generally slim-skulled pterosaurs of the later Jurassic. Its teeth were varied, suggesting it may have had a more mixed diet than the pure fish-eaters. And then there was Archaeopteryx. In the rocks of the Solnhofen limestone formation in what is now Bavaria, Germany, deposited in shallow tropical lagoons approximately 150 million years ago, lie some of the most celebrated fossils in the entire history of paleontology. The fossils of Archaeopteryx. 11 specimens have been recovered over the years since the first was described in 1861, and each one is extraordinary. The limestone that preserved them is fine-grained enough that it captures not just the bones but the impressions of feathers, preserved in exquisite detail, the individual barbs visible in the best specimens. Archaeopteryx was approximately the size of a crow or a small raven. It had a full set of teeth in its jaws like a theropod dinosaur. It had a long bony tail like a theropod dinosaur. It had clawed hands on its wings like a theropod dinosaur, but it also had asymmetric flight feathers arranged on its wings in a pattern consistent with the feathers of modern flying birds, and the musculature implied by its shoulder and chest bones suggests it could achieve powered, flapping flight, not just gliding. Archaeopteryx represents the moment when the dinosaur lineage and the bird lineage are essentially the same thing. It is a doorway, an evolutionary transition captured in stone, the first page of the birds written in the rock of an ancient lagoon. From Archaeopteryx and animals like it, every bird alive today descends. Every sparrow and eagle and penguin and hummingbird is, in the technical biological sense, a dinosaur, not like a dinosaur, not descended from dinosaurs. A dinosaur carrying in its body and its behaviour and the structure of its bones the inheritance of a lineage that stretches back, unbroken, to the small bipedal opportunists that survived the Carnian pluvial episode. The geological setting of the Jurassic world was also transforming in ways that would drive dinosaur evolution forward in new directions. Pangaea was breaking apart. The supercontinent that had dominated the planet's geography since before the beginning of the dinosaur story was fracturing along deep rifts, driven by the same kinds of mantle forces that had triggered the great volcanic episodes of the Triassic. The Proto-Atlantic Ocean was widening year by year, centimetre by geological century, separating what would become North America from what would become Africa and Europe. To the south, the great southern supercontinent called Gondwana was also beginning to fragment, as Africa and South America began their slow drift away from each other, and from Antarctica and Australia and India. These newly separating landmasses created new coastlines and new shallow seas, new habitats to be colonized, new environments to be adapted to. Isolated populations of dinosaurs on separating continents began to diverge, evolving in different directions without gene flow connecting them to the rest of the world's dinosaur populations. The Jurassic world was, by any measure, one of the most magnificent this planet has ever supported. Its scale alone is humbling. The forests of giant conifers stretching for thousands of miles across the floodplains and mountain slopes and coastal lowlands of the now fragmenting supercontinent. The rivers flowing broad and warm through those forests, their banks tracked by the enormous footprints of sauropods and smaller footprints of 100 other species. The shallow eparic seas spreading across continental interiors, their warm clear waters full of ammonites and ichthyosaurs and the sleek powerful early plesiosaurs. The pterosaurs riding the thermals above everything, looking down on a world that from above must have seemed like an endless green and brown tapestry, stitched with the silver threads of rivers and the blue of lakes. And everywhere in that tapestry, the dinosaurs. Not just the giants, though the giants define the age in the imagination, but the full, extraordinary diversity of them. The small, fast theropods hunting through the undergrowth, the mid-sized predators patrolling the forest margins, the stegosaurs moving in their slow armoured dignity across the open ground between forest patches, the early ornithopods grazing on low-growing vegetation along the river margins, the long-necked sauropods everywhere, always, their footfalls a constant percussion in the ground, their presence as fundamental to the Jurassic landscape as the conifers themselves. This was the Golden Age, Not because it was the most diverse or the most complex, those records would belong to the Cretaceous that followed, but because it was the period when the dinosaurs first truly inhabited the world, when they first filled it completely from top to bottom, from the largest animal that has ever walked on land to the smallest quick-footed hunter in the dark beneath the ferns. They had inherited the Earth, and what they had done with it was magnificent. Let the Jurassic forest settle around you in the dark. Let the deep ground vibrations of the sauropod herds carry you down into rest. The sounds are slow and immense and ancient and perfectly safe. Everything here is at peace. Everything here is full of the unhurried grandeur of geological time. Breathe slowly, the story continues. 145 million years ago, something small and quiet appeared in the world. Not a great predator, not a geological catastrophe, not a new ocean or a new mountain range. What appeared was a flower, or more precisely the ancestor of a flower, a small, unremarkable seed-bearing plant that, unlike the conifers and cycads and tree ferns that had dominated the plant world for hundreds of millions of years, enclosed its seeds within a protective fleshy structure, and, more significantly, produced small reproductive structures that attracted insects and other animals to visit them, and in doing so carry pollen from one individual to another. These were the first angiosperms, the first flowering plants, and their appearance and spread during the early Cretaceous period was one of the most transformative events in the entire history of life on land. The Cretaceous period runs from 145 million years ago to 66 million years ago, a span of nearly 80 million years. Within that span, the world underwent changes more varied and more thorough than at almost any equivalent period before it. Continents continued their drift toward configurations increasingly resembling the modern world. Climates shifted and varied and shifted again. Sea levels rose and fell dramatically, covering vast areas of continental interior with shallow warm seas and then withdrawing again. The planet that existed at the end of the Cretaceous looked genuinely more like the planet we live on today than at any previous point in the history of the dinosaurs. And through all of it, the dinosaurs diversified into forms so spectacular, so varied, so apparently boundless in their evolutionary creativity, that the Cretaceous world produced what may well be the most diverse and complex terrestrial ecosystem in Earth's entire history. The flowering plants drove much of this transformation, so it is worth pausing to understand what made them so revolutionary. Before the angiosperms, the plant world of the Mesozoic was dominated by species that did not invest heavily in attracting visitors. Conifers pollinated by wind, releasing vast clouds of pollen and relying on chance to carry it to receptive female cones. Cycads used simple mechanisms. Ferns produced spores rather than seeds. The relationship between plants and animals was important, but not the intricately co-evolved, mutually dependent web of exchange that the flowering plants were about to introduce. A flower is, in one sense, an advertisement. It is a structure built entirely around the purpose of attracting a specific visitor, usually an insect but sometimes a bird or a bat or some other animal, close enough to pick up pollen from the plant's stamens and then carry that pollen to another plant of the same species. In exchange for this pollination service, the flower offers a reward, usually nectar, a concentrated sugar solution, sometimes nutrient-rich pollen itself. The relationship is one of mutual benefit, the plant getting its pollen transported with far greater accuracy and efficiency than wind could provide, the visitor getting a reliable food source in return. What makes this relationship so evolutionarily powerful is that it can become increasingly specialized over time. As a particular plant species evolves a more distinctive flower shape or scent or color, it attracts a more specific set of pollinators. As those pollinators evolve in response to the flowers they visit, they become more efficient at collecting the rewards those specific flowers offer. The two lineages, plant and pollinator, co-evolve, each driving the other toward greater specialization, greater mutual dependency, greater efficiency of the relationship. Over millions of years, this process produced the extraordinary diversity of flowers and pollinators that we see in the modern world. But its effects in the Cretaceous were already profound. As angiosperms diversified and spread, first along riverbanks and disturbed ground where their fast growth gave them an advantage over slower-growing conifers, then outward into forests and uplands and every accessible environment, The insects that pollinated them diversified alongside them. The Cretaceous saw an explosion of bee-like and wasp-like insects, butterfly and moth lineages, fly families, beetle groups, all diversifying in biological lockstep with the diversifying flora. The world's plant communities, which had been relatively uniform in colour through the age of conifers and ferns, began to produce explosions of colour and scent, flowers in red and yellow and white and purple, and combinations that only insects with ultraviolet vision can appreciate. Fragrances drifting on the warm Cretaceous air, complex organic molecules advertising nectar to visitors with chemical senses incomparably more acute than any human nose. And then came the fruits. Fruits were the angiosperm's answer to a different problem: seed dispersal. Once a seed is fertilized, the plant needs to get it away from the parent plant, where it will compete with the parent for light and water and nutrients. Wind dispersal works for some seeds. Water dispersal works for others. But the most effective seed dispersal agents are animals, which carry seeds inside their digestive systems and deposit them, along with a package of fertilizer, sometimes considerable distances from the parent plant. Fruits were the plant's payment for this dispersal service. A fleshy, nutritious structure wrapped around the seed evolved to attract animals large enough to carry the seed away before depositing it elsewhere. Dinosaurs ate fruits. Early mammals ate fruits. Birds ate fruits. All of them, in eating the fruits, were serving as the plant's transportation network, carrying seeds across the landscape and planting them with every step away from where they had fed. The Cretaceous world, driven by the flowering plant revolution, was a world of unprecedented ecological complexity, and the dinosaurs that lived in it were the most diverse array of large land animals Earth had ever produced. The hadrosaurs, often called duck-billed dinosaurs because of the broad, flattened ends of their snouts, were among the most successful and most numerous of the large Cretaceous herbivores. They were remarkable animals in ways that reward careful attention. Hadrosaurs had dental batteries, not individual teeth but dense masses of teeth packed together into grinding surfaces. A single hadrosaur jaw could contain several hundred individual tooth elements, all packed together and replacing each other from below as the upper surface wore away, like a conveyor belt of teeth. The grinding surface this arrangement created was extraordinarily effective for processing tough, fibrous vegetation. Hadrosaurs could eat plant material that most other herbivores found too difficult to process, including tough conifer needles and bark, which gave them access to food sources that their competitors could not fully exploit. Many hadrosaurs also had extraordinary crests on their heads. Parasaurolophus is perhaps the most famous. Its crest was a long, hollow tube that swept backward from the top of its skull, sometimes reaching lengths of several feet, curving back over the animal's neck and shoulders. This crest was not solid. It was hollow, connected internally to the nasal passages, forming a resonating chamber through which air could be forced to produce deep, low-frequency sounds. Research modelling the acoustic properties of Parasaurolophus crests suggests that this animal could produce calls in the frequency range that travels most efficiently through dense forest, low enough to penetrate thick vegetation, distinctive enough in pitch and timbre to be recognisable to other members of the species at significant distances. Imagine standing at the edge of a late Cretaceous forest as a herd of Parasaurolophus moves through the deep shade beneath the canopy. You hear them before you see them. A deep, resonant sound that you feel as much as hear. A low vibration in the air that seems to come from everywhere at once, because it has been reflected and transmitted by every tree trunk and every dense stand of vegetation between you and the animals producing it. It is not alarming. It is beautiful in a way that has no word in any human language, a sound no human ever heard in their living lifetime, a sound extinct for 66 million years, and then suddenly present again in the reconstruction of a scientist's model. The ceratopsians were another extraordinary group that reached their peak diversity and abundance in the late Cretaceous. Ceratopsians were the horned and frilled dinosaurs, and within that broad description lies a diversity of forms that staggers the imagination when you begin to enumerate them. Triceratops, the most familiar, had 3 horns, one on its nose and one above each eye, and a large bony frill extending behind its skull. Styracosaurus had a nose horn surrounded by a frill that bore 6 long bony spikes, projecting outward from its edge, creating an intimidating silhouette. Pachyrhinosaurus had a broad, rough nasal boss instead of a nose horn, perhaps for shoving contests within the species. Cosmoceratops, from the late Cretaceous of what is now Utah, had 15 separate horn-like structures on its skull, more than any other known horned vertebrate. The elaborateness of these head ornaments, their variety, their evident evolutionary energy, tells us something important about the social lives of these animals. Structures this complex and this energetically expensive to produce do not evolve simply for predator defense, though they may have served that purpose secondarily. They evolve primarily through sexual selection and social signaling, through competition within the species for mates and status and territory. The ceratopsians were complex social animals, capable of individual recognition, of status competition, of mate choice, of behaviours subtle enough to make the difference between an individual that reproduced and one that did not. The Tyrannosaur lineage represents one of the great evolutionary stories of the Cretaceous. The Tyrannosaurs had modest beginnings. Early Tyrannosaurs from the Middle Cretaceous were relatively small, long-armed, and not obviously predestined for the spectacular forms they would eventually produce. Proceratosaurus from the Middle Jurassic of what is now England was a relatively small theropod with a small horn on its snout. Guanlong from the late Jurassic of what is now China was similarly modest in size but bore an elaborate cranial crest. These early tyrannosaurs were not yet the apex predators they would become. Through the Cretaceous, the tyrannosaur lineage underwent a dramatic transformation in size and ecological role, particularly in the northern hemisphere continents where their fossils are most abundantly found. By the late Cretaceous, tyrannosaurs had become the dominant large predators of North America and Asia, and they had achieved a size and anatomical specialization unprecedented in the theropod lineage. Tyrannosaurus rex lived in what is now Western North America during the very last part of the Cretaceous, approximately 68 to 66 million years ago. It was, by some measures, the most powerful land predator that has ever existed. Its skull was massive, among the largest and most heavily constructed predator skulls in the history of land life, roughly 5 feet long in large individuals, deep and wide and reinforced with thick bone, capable of generating bite forces that could crush the bones of large dinosaurs. Its teeth were not blade-like in the way that many other theropod teeth were. They were more like railroad spikes, thick and conical, and designed not for slicing but for crushing, for breaking through bone and extracting the marrow within. Its arms have been the subject of much comment because they are so dramatically reduced in size relative to the body, seemingly tiny against the massive body they are attached to. But those arms, though small relative to the rest of the animal, were not weak. The musculature suggested by the arm bones indicates that a Tyrannosaurus arm could have bent at the elbow to lift loads of several hundred pounds. They were not vestigial. But whatever function they served in the living animal, it was not the same function that the long, grasping arms of earlier theropods served. Tyrannosaurus rex was approximately 40 feet long and weighed somewhere between 8 and 15 tons in life, the range reflecting the difficulty of reconstructing soft tissue mass from skeletal remains. It moved on 2 immensely powerful legs that left footprints in the ancient mud now preserved in rock, across Montana and South Dakota and Wyoming, and Alberta and Saskatchewan. It was probably a pursuit predator for smaller prey, and an ambush predator, or pack hunter, for very large prey, though questions about its precise hunting behaviour remain. What is clear from the fossil record is that Tyrannosaurus rex was not alone in its late Cretaceous world. It shared that world with the ceratopsians, with enormous armoured ankylosaurs, with hadrosaur herds that may have numbered in the thousands, with small feathered theropods hunting insects and small mammals in the undergrowth, with mammals themselves becoming slightly less marginal, slightly less purely nocturnal, slightly more diverse in their exploration of Cretaceous ecological space. The Cretaceous world was also profoundly shaped by its geography. The continents had drifted to positions much closer to their modern locations. North America was still connected to Europe and Asia via land masses at high latitudes, creating corridors for animal movement. South America, Africa, India, Australia, and Antarctica were increasingly isolated, each developing its own distinctive dinosaur fauna as isolation drove evolutionary divergence. The shallow inland seas that spread across many continental interiors during the Cretaceous created profound geographic barriers on the continents themselves. The Western Interior Seaway, which at its maximum extent divided North America down the middle from the Gulf of Mexico to the Arctic Ocean, created a western landmass called Laramidia and an eastern landmass called Appalachia, each of which developed its own dinosaur community. The result was a world of extraordinary biological diversity, a world where every continent and every major subregion was producing its own distinctive array of dinosaurs, its own versions of the large predator role, its own versions of the large herbivore role, its own experiments with armour and horns and crests and frills. The Cretaceous was the age of dinosaur diversity in its fullest and most exuberant expression. The world was humming with life at every level, from the flowering plants and their pollinators at the base, through the enormous complexity of insect communities, through the small mammals and lizards and early birds and frogs and salamanders, through the mid-sized dinosaurs, through the great herds of hadrosaurs and ceratopsians, up to the apex predators at the top. It was the most complex terrestrial ecosystem in Earth's history. And the dinosaurs were everywhere in it. Let that image settle over you as you breathe slowly in the quiet dark. The Cretaceous world humming and alive, the flowers opening in the morning light, the insects moving between them, the hadrosaurs calling to each other through the forest with their deep resonant crests, the ceratopsians moving in their thousands across the coastal plains, and somewhere in the deep forest shadow, the slow, deliberate movement of something very large and very old. Rest. The story is not done yet. There is still so much to see. Step away from the giants for a moment. Step back from the enormous sauropods and the apex tyrannosaurs and the great herds of hadrosaurs and ceratopsians. Step back until all of those magnificent, enormous creatures recede into the background of the landscape, still visible, still present, still fundamental to the world you are standing in, but no longer filling your entire field of attention. Now look at what else is here. Because the world of the dinosaurs was not simply a world of giants. It was a world of extraordinary complexity at every scale, a world woven together from millions of interacting species, ranging from the largest land animals that ever lived all the way down to the invisible microscopic organisms in the soil. Understanding the dinosaurs means understanding the whole ecosystem they built and inhabited and depended on, not just the famous ones, but the whole vast, intricate living system of the Mesozoic world. Look down first, at the ground. The soil of the Mesozoic world was not like the soil we know today. Modern soils are built in large part by the root systems of flowering plants and by the extraordinarily diverse communities of fungi and bacteria and invertebrates that process organic matter in the topmost layers. The Mesozoic soils, particularly those of the Triassic and Jurassic, were built by different organisms in different configurations, but they were still complex, still full of life, still the foundation of everything above them. Earthworms were present. Millipedes and centipedes processed dead plant material in the leaf litter. Beetles, by the Cretaceous the most species-diverse animal order on the planet, burrowed and chewed and tunneled through every layer of the soil profile. Termites, which appeared in the Cretaceous, were beginning to develop their extraordinary wood processing capabilities. The fungi that formed symbiotic relationships with plant roots, helping those roots absorb phosphorus and water in exchange for sugars, were present and active, invisible threads of connection running between every plant in the forest. The soil of a Cretaceous forest was alive in ways we are still only beginning to appreciate. A single handful of that ancient soil, if we could hold it, would contain millions of bacteria, thousands of fungal threads, hundreds of nematodes, dozens of small invertebrates, all interacting, all processing, all converting dead matter into nutrients and nutrients into living tissue in an endless cycle. Now look at the plants. The plant communities of the Mesozoic world changed dramatically across the 165 million years of the dinosaur era. The Triassic plant world was dominated by seed ferns and primitive conifers and cycads and horsetails. The Jurassic plant world was dominated by more advanced conifers, by tree ferns and ground ferns, by cycads and ginkgos and a variety of seed plants. The Cretaceous plant world, increasingly dominated by the spreading angiosperms, was visually richer and more varied than anything that had existed before. Imagine a Cretaceous forest in the late afternoon light. You are somewhere in what is now western North America, in the warm, wet coastal lowlands that lined the western shore of the Western Interior Seaway approximately 75 million years ago. The air is warm and intensely fragrant. The fragrance comes from everywhere at once, from the flowering trees above you, some bearing blossoms in shades of white and pale yellow that drift down occasionally on the warm currents of air, from the dense flowering undergrowth at your feet, from the decomposing leaf litter and the wet soil and the fungal networks threading through it all. The forest around you is stratified. Tall conifers still stand in the canopy, their dark tops catching the afternoon light, their trunks rising 60 or 70 feet before branching. But now, woven between and among those conifers, are angiosperms, broadleaf trees with large flat leaves that catch more light than the needle-like conifer leaves beside them. Some are already large, their trunks thick and their canopies spreading. Others are younger, pushing up through gaps in the forest wherever a fallen tree or a small clearing has let light reach the ground. The understory is dense, flowering shrubs fill the spaces between the larger trees. Ferns still cover much of the ground, but they are interspersed with flowering herbaceous plants, early members of lineages that will one day include daisies and lilies and orchids and an uncountable multitude of other flowering plant families. The ground is never quite dry here. The soil is dark and deep and rich. Now look at the insects. The insect life of the Cretaceous world was already extraordinarily diverse. Amber, fossilized tree resin preserves it for us in extraordinary detail. Cretaceous amber has been found containing insects preserved in 3 dimensions, their bodies intact down to individual hair and eye facets, a gallery of the living world from 70 or 80 or 90 million years ago. What it shows us is an insect world already rich with familiar forms. Ants, which appeared in the early Cretaceous and would eventually become, by some measures, the most ecologically dominant animals on Earth. Bees, co-evolving with the spreading angiosperms, termites, beetles, flies, moths and butterflies, lacewings, dragonflies and damselflies, crickets and their relatives, wasps. The insect world of the Cretaceous was probably louder and more intensely alive with movement than anything we experience today. Imagine the sound of a hot summer afternoon in a temperate forest, multiplied by an order of magnitude, and you begin to approach what the ambient acoustic environment of a Cretaceous forest probably sounded like. Every branch and every leaf in constant motion, with the movement of small bodies. Every flower attended by multiple visitors simultaneously. Every fallen log covered in species feeding on the wood and on each other. Now look at the smaller vertebrates. The Cretaceous world was full of small vertebrates at every ecological level. Lizards were present and diverse, ranging from insect hunters no longer than a human hand to animals approaching the sizes of modern monitor lizards. Early snakes had appeared by the late Cretaceous, their fossils still rare and fragmentary, but their presence confirmed, elongated, limbless hunters threading through the undergrowth. Frogs and salamanders inhabited every wet habitat, their populations immense in the warm, productive environments that the Cretaceous climate supported in the lower latitudes. The mammals deserve special attention. For the entire 165 million years of the dinosaur era, mammals were present. They were there from the beginning, evolved from the cynodont synapsids that had survived the Permian extinction and the Triassic world. They were there through the Jurassic, hidden and quiet and mostly small. They were there through the Cretaceous, growing slightly more diverse as the world's complexity increased, but never, during the dinosaur era, achieving the ecological significance that they would later demonstrate. Cretaceous mammals were for the most part small. Many were probably no larger than modern mice or rats. Some were slightly larger, comparable to smaller possums or shrews or hedgehogs. They were overwhelmingly insectivorous or omnivorous, feeding on insects and worms and small invertebrates and perhaps occasional plant material. Most were probably nocturnal, active at night when the cold-blooded predators and many of the diurnal dinosaurs were resting, exploiting the hours of darkness as an ecological niche that the reptile-dominated world had left relatively underfilled. But they were evolving. Slowly, persistently, in the background of a world owned by others, the mammals were accumulating the adaptations that would one day make them the dominant large animals on Earth. More sophisticated teeth, capable of precise cutting and grinding in ways that let them process a wider variety of foods. Larger brains relative to body size, associated with more complex behaviors and more flexible responses to novel situations. More advanced hearing, with the 3 tiny bones of the mammalian middle ear, evolved from bones that in their ancestors had been part of the jaw, providing sound perception of extraordinary sensitivity. These adaptations were building, generation by generation, in the small furry creatures that scurried through the undergrowth while Tyrannosaurus rex walked overhead. Now look at the birds. By the Cretaceous, birds had become a diverse and ecologically significant group. They had expanded far beyond the primitive Archaeopteryx-grade ancestors of the late Jurassic. Enantiornithine birds, a group that has no modern survivors, but that was the dominant bird lineage for most of the Cretaceous, were extraordinarily diverse. They range from tiny insect catchers to fish eaters with wingspans of several feet. They had clawed wings like their theropod ancestors, unlike modern birds. They laid eggs in trees and on the ground. They filled ecological roles occupied by modern birds, perching in the canopy, diving for fish in lakes and rivers, probing the ground for invertebrates. The modern bird lineage, the one that would produce all surviving birds today, was also present and diversifying in the Cretaceous. Early members of the groups that would give rise to ducks and geese, to shorebirds, to primitive forms related to modern chickens and their relatives, were present in late Cretaceous deposits. They were becoming established, laying the groundwork for the explosive diversification that would follow the extinction. Now look at the feathered dinosaurs. Because by the Cretaceous, many theropod dinosaurs were feathered, and the line between a non-avian feathered dinosaur and an early bird was not as clear as we once imagined. Microraptor, from the early Cretaceous of what is now China, was a small feathered dinosaur about the size of a crow that had flight feathers not just on its arms, but also on its hind legs, effectively 4 wings. It was probably capable of gliding and possibly some degree of powered flight. Genyuan was a sickle-clawed dromaeosaur with large, well-developed flight-quality feathers on its wings, though its body size suggests it could not fly. Anchiornis was a small, delicately built feathered dinosaur whose feathers have been analysed for pigment chemistry, revealing a black and white patterning with a reddish crest, the coloration of an animal we have never seen alive rendered in the colours it wore in life 75 million years ago. The feathered dinosaurs of the Cretaceous range from tiny insect eaters to large, powerful predators. Yutyrannus, a relative of the tyrannosaur lineage from the early Cretaceous of China, was an animal approximately 30 feet long, bearing a coat of long, filamentous feathers across much of its body. This was not a small bird-like animal. This was a substantial predator, wearing feathers not for flight but for insulation and possibly display, its bulk softened visually by the long filaments that covered it. Imagine encountering Yutyrannus in a cold early morning in the Cretaceous forest of what is now northeastern China. The mist is thick and low, barely clearing the tops of the undergrowth, filtering the pale early light into something silver and gentle. The forest is quiet, the insects not yet active, the birds not yet calling. And then through the mist comes a sound you feel before you hear it, a low, deep exhalation, and then the movement of something large between the trees. Yutyrannus steps into the small clearing where you are standing, its long feathers damp with the morning moisture, its large eyes oriented forward with the binocular vision of a predator, its breath visible in the cold air as slow, regular puffs. It looks at you for a moment with those forward-facing eyes. Then it moves on, unhurried, disappearing back into the mist. The ecosystem of the dinosaur world was not simply large animals eating large plants. It was an intricate, layered, mutually dependent web of interactions involving millions of species, from the microorganisms in the soil to the apex predators at the top. It was a world where the angiosperms and their pollinators were reshaping the plant communities from the bottom up, where the insects were processing energy and nutrients through 1,000 different ecological pathways, where the small feathered dinosaurs and early birds were turning insects into protein for larger predators, where the mammals were quietly accumulating the adaptations they would need when their moment finally came. The dinosaurs were not a world unto themselves. They were the largest and most visible threads in a tapestry of extraordinary complexity, and they were woven through and through with everything else that shared their world. Understanding them means understanding the whole of it. The deep soil teeming with invisible life, the insect communities filling the air with sound and motion, the flowering plants painting the forest in colours that had never existed before, the small mammals and feathered dinosaurs threading through the undergrowth, the rivers full of fish and early turtles and small crocodilians, the coastal waters full of marine reptiles hunting the abundant fish and invertebrates of the warm Cretaceous seas. All of it was the dinosaur world. All of it was the most complex and varied terrestrial system this planet had ever supported. And in the middle of it, breathing the warm, flower-scented Cretaceous air, was you, a visitor from an incomprehensibly distant future, standing in the ancient forest with the sounds of the most successful land animal empire in the history of Earth all around you. Breathe slowly. Let the warmth of the Cretaceous afternoon rest on your skin. Let the sounds of the forest fill the quiet around you, the insects, the distant calls of hadrosaurs, the wind in the canopy, the soft percussion of rain beginning on the broadleaves above. You are perfectly safe here, you're resting here, and the story is not done. There are evenings near the end of summer when the light changes in a way that is difficult to describe but impossible not to feel. The days are still warm, the flowers are still blooming, the trees are still in full leaf, their canopies dense and green, still catching the afternoon sun and turning it into that particular golden late summer warmth that feels like abundance, like richness, like a world at the height of its expression. Everything looks the same as it did in June. Everything looks the same as it has for months. And yet there is something in the angle of the light, something in the quality of the shadows in the late afternoon, that tells you, without words, without any conscious analysis, that this is the fullness, not the beginning. That the world is still beautiful, still warm, still humming with life, but that it is also, very gently, beginning its turn towards something else. The late Cretaceous world, in the millions of years before the Great Extinction, had something of that quality about it. Not tragedy, not obvious decline, not the dramatic collapse that might seem in retrospect like it should have been clearly visible to anything intelligent enough to read it. The late Cretaceous was in many ways the most magnificent the dinosaur era had ever been. The hadrosaurid herds were at their most diverse. The ceratopsian lineage had produced some of its most spectacular forms. Tyrannosaurus rex, the most powerful land predator in Earth's history, was alive and hunting in the forests and floodplains of what is now Western North America. The birds were diversifying rapidly. The flowering plants had spread to cover most of the world's vegetation. By most metrics, the late Cretaceous was not a world in crisis. It was a world at the peak of its expression. And yet, beneath the surface, things were changing. Slowly, persistently, with the patient, deep-time rhythm of geological forces operating on scales that no individual animal, however long-lived, could possibly perceive. The Deccan traps were erupting. This volcanic province, located in what is now central and western India, had been building its eruptions through the latest Cretaceous, producing massive volumes of flood basalt lava and releasing significant quantities of carbon dioxide and sulfur dioxide into the atmosphere. The Deccan eruptions were not as sudden or as intense as the event that would eventually end the Cretaceous. They did not produce the kind of catastrophic, immediate global disruption that a different kind of event would, but they were real, they were ongoing, and they were adding stress to the global climate system in ways that the fossil record has preserved. Global temperatures were variable in the latest Cretaceous, with some evidence for both warming phases, driven by the Deccan carbon dioxide emissions, and cooling phases driven by the sulfur aerosols from the same eruptions. Sea levels were changing. The western interior seaway of North America, which had divided the continent for much of the Cretaceous, was gradually receding as sea levels slowly dropped, reconnecting the eastern and western parts of the continent and allowing the movement of species across what had been a marine barrier. These changes were affecting the dinosaur communities of the latest Cretaceous in ways that the fossil record records, though the interpretation of those records is a subject of ongoing scientific discussion. Some researchers see evidence of declining dinosaur diversity in the last few million years of the Cretaceous, particularly in North America, where the record is most complete. Some large dinosaur groups that had been diverse and abundant in the earlier late Cretaceous become less diverse, their range of species narrowing in the final millions of years. Whether this represents genuine ecological stress from the changing climate, or simply the natural turnover of species in a dynamic ecosystem is debated. But it is worth spending some time in the late Cretaceous world, in those last few million years, simply appreciating it. Because whatever the trajectory of certain groups in the final chapter of the Cretaceous, the world itself remained extraordinary. Imagine the coastal lowlands of what is now Montana and Alberta, approximately 66 million years ago, the last autumn before the end of the dinosaur era, a world that does not know what is coming, a world that is simply living, as it has been living for 165 million years, with the completeness and the unconscious fullness of a living system. The season is autumn here, and the deciduous angiosperms have turned the forest into something that has never existed before in the history of the world. Because for most of the dinosaur era, there were no deciduous trees in the sense we know them. The transition to seasonal colour, the annual turning of leaves from green to gold and orange and red, is tied to the spread of the flowering plants and to the development of their deciduous habit, the shedding of leaves during the cold or dry season to conserve water and nutrients. By 66 million years ago, this process was well established in the higher latitude forests, and the result was a spectacle of colour that would not have looked entirely out of place in a modern New England autumn. The hadrosaurs are moving through this transformed forest in large groups, their movements raising the smell of crushed leaves and wet soil that is both ancient and familiar. They are feeding on the abundant late-season plant material, storing energy for whatever winter adaptation they have evolved, their crests occasionally producing low, resonant calls that travel through the trees and echo off the distant hills. Triceratops moves at the margins of the forest and the open ground, its great three-horned head swinging slowly from side to side as it crops the low-growing flowering plants with its parrot-like beak. It is a large individual, perhaps 25 or 30 years old, the slow bone growth of its mature years adding solidity and thickness to the frill that once was thin and brightly marked. It is experienced and settled, its senses tuned by decades of predator awareness, its movements deliberate and unhurried. Somewhere in the forest, perhaps half a mile away, perhaps more, something very large is moving. The ground carries the vibration of it, slow and rhythmic, more felt than heard. Tyrannosaurus rex is abroad in the October forest, moving with that measured, heavy deliberateness, its tiny arms folded against its chest, its enormous tail held out behind as a counterbalance to the massive head swinging at the other end of its body. It is not hunting urgently. It does not need to. It is the largest predator in the world, and the world is full of food. The air smells of autumn, of leaf mould and cold mud, and the distant chemical signature of the river to the east, running cold and clear between its banks. The skies are deep, rich blue, the kind of blue that only appears in a clean atmosphere on a cold, bright autumn day, and the light is golden and low, striking the turning leaves at an angle that makes them seem lit from within, as though each one is carrying its own small fire. This is the world 66 million years ago, this specific day, this specific autumn afternoon. The flowers are blooming in the lower story of the forest, where enough light still reaches the ground through the canopy. The insects are still busy among them, though the cold nights are slowing them, and in a few weeks most of the adult insects will be dead or dormant, their eggs waiting in the soil and under bark for the spring that will come, though neither they nor anything else in this world can know what that spring will look like. Small mammals are moving through the undergrowth with the increased urgency of animals that know, in the wordless bodily language of evolution, that winter is near and stored fat is survival. Early birds perch in the high branches, some of them beginning the restlessness that will in a few weeks drive them southward. High in the sky, invisible to the forest below, the atmosphere is pure and clean and cold. There is no smoke in it, no chemical disruption. The Deccan eruptions are real and ongoing, but on this particular afternoon, in this particular place, the sky is clear and vast and empty. Somewhere in the outer darkness of space, approximately 60 million miles away, a chunk of rock and ice the size of a small city is moving. It has been moving for hundreds of millions of years. Its orbit around the sun is long and eccentric, swinging it in from the outer solar system and back out again in a slow, patient loop. It has made this journey countless times. It will never make it again. But none of that is visible in the October forest. None of that is felt in the ground trembling under Triceratops' feet, or in the air carrying the calls of the hadrosaur herd. None of that is present in the golden afternoon light falling on the turning leaves. The world is simply alive, fully, magnificently alive, buzzing and calling and growing and dying and eating and breathing and reproducing, as it has been for 165 million years. It is a Tuesday, or a Wednesday, or some day that has no name, in a world without days or names, in a time so deep that our language for time begins to fail us. It is an ordinary day. There have been many ordinary days in the long, quiet, spectacular history of the dinosaur empire. 165 million years of ordinary days, each one full of living and dying and the patient work of existence. This one, the October afternoon in the Montana forest 66 million years ago, is not visibly different from any of the others. But it is one of the last. Let that thought drift past you gently and without grief, because this is not a story about loss. It is a story about transformation. It is a story about the deep, patient, endlessly creative processes of a living planet. And those processes do not end. They do not end. Rest. Breathe. The last Cretaceous autumn is beautiful around you, and the story is almost complete. 66 million years ago, on an ordinary Tuesday or Wednesday or unnamed day in the late Cretaceous world, something changed. Not slowly, not gradually, not in the way that the Carnian pluvial episode had changed the world, in a long, steady building of different conditions that accumulated over millions of years into a new normal. This was different. This was the kind of change that happens in a single day, in a single moment, in the fraction of a second when a piece of rock 12 kilometers wide, traveling at roughly 70,000 kilometers per hour, struck the shallow coastal waters of what is now the Yucatan Peninsula of Mexico, and detonated with an energy release equivalent to roughly 10 billion of the most powerful nuclear weapons humanity has ever built. The Chicxulub impactor. The collision happened on that ordinary day with such force that the rock itself and a substantial volume of the Earth's crust where it struck were instantly vaporized. The energy release was so enormous that the shockwave traveled around the entire planet several times. Earthquakes on a scale never experienced before or since radiated outward from the impact site. Massive tsunamis, walls of water hundreds of feet high, surged outward across the oceans and crashed into coastlines thousands of miles from the impact site. The entire Gulf of Mexico was, for a brief period, effectively set in motion by the force of that impact. And then the sky filled. The vaporized rock and superheated gases launched by the impact rose into the stratosphere in a column of debris that spread around the entire planet within days. Tiny particles of rock and soot and sulfuric acid droplets, billions of tons of them, diffused through the upper atmosphere and formed a global veil. The sun's light filtered through this veil was reduced, not merely dimmed. In the worst of it, in the weeks and months immediately following the impact, the surface of the Earth was receiving less sunlight than it needed to sustain photosynthesis. Photosynthesis is the foundation of almost all life on the surface of this planet. Take it away, and the food web collapses from the bottom. Plants die. The animals that eat plants die. The animals that eat those animals die. The winter lasted months, perhaps longer. Temperatures plunged in the most affected regions. Frost came to latitudes that had not seen frost in millions of years. The food webs of the terrestrial world collapsed, with a speed that makes the 2 million year Carnian pluvial episode look gradual by comparison. The non-avian dinosaurs died. Not instantly, not in a day. The process took months and years, the populations declining as food sources disappeared, as breeding success fell, as the cold killed animals adapted to the warm Cretaceous world. But geologically, it was instant. The boundary between the last layer with non-avian dinosaur fossils and the first layer without them is, in the rock record, a thin dark line. A clay layer enriched with iridium, an element rare in Earth's crust but abundant in asteroids, laid down across the entire planet simultaneously as the Chicxulub debris settled from the atmosphere. Below that line, the Cretaceous, the dinosaurs, the world that had existed for 165 million years. Above that line, the Paleogene, the aftermath, the empty world. In the immediate aftermath, the planet was quieter than it had been in 165 million years. The great sauropod lineages, already extinct by this point, had left their silence behind long before. But now the hadrosaur herds were gone, the ceratopsian groups were gone, the tyrannosaurs and their relatives were gone. The enormous variety of theropods and ornithopods and ankylosaurs and pachycephalosaurs, the whole magnificent, noisy, populous dinosaur empire was gone from the land. The marine world had also suffered catastrophically, The mosasaurs, the plesiosaurs, the marine crocodilians were largely or entirely gone. The ammonites, those coiled cephalopods that had been a constant presence in the world's oceans since before the dinosaurs existed, went extinct. Marine ecosystems that had been building in complexity for the entire Mesozoic era were profoundly disrupted. And yet, life did not end. In burrows beneath the ground, small mammals had survived. Their small bodies required less food. Their omnivorous diets gave them more options when specific food sources failed. Their warm-bloodedness let them stay active in the cold. Their ability to reproduce quickly, multiple offspring multiple times per year, meant that populations that survived could rebuild rapidly. In the trees and on the ground, the birds had survived. Not all birds. Many Cretaceous bird lineages went extinct along with everything else. But the modern bird lineage, the ancestors of all living birds, made it through. Their small bodies, their efficient metabolisms, their ability to eat seeds and invertebrates that remained available even in the post-impact world, kept them alive through the worst. In the rivers and lakes and seas, fish and amphibians and turtles and crocodilians survived. Marine fish communities were disrupted but not destroyed. Freshwater ecosystems, somewhat buffered from the worst of the atmospheric disruption, fared better than terrestrial ones. The planet was not dead. It was damaged, diminished, simpler than it had been. But it was not dead, and it never had been, not in the 4.5 billion years of its history, and it was not going to be now. What followed the end Cretaceous extinction was one of the most extraordinary evolutionary explosions in the history of complex life. The mammals, freed from 66 million years of ecological constraint, freed from the competitive pressure of the dinosaurs that had kept them small and marginal and mostly nocturnal for their entire history, exploded into the empty world with a speed and creativity that is astonishing even by the generous standards of evolutionary radiations. Within 10 million years of the extinction, a time period that seems long in human terms but is a geological eye blink, mammals had diversified from small insectivores into a range of body forms and ecological roles that is breathtaking. Large herbivores appeared, large predators appeared, animals that ate fish appeared, animals that climbed trees and ate fruit appeared, animals that ran on the open plains appeared, animals that returned to the sea appeared. Within 20 million years, the ancestors of every major modern mammal group had appeared. The ancestors of whales, the ancestors of horses and rhinoceroses and elephants, the ancestors of bats, the ancestors of the primates that would eventually, through millions of years of further evolution, produce the apes, and among the apes the human lineage. Every mammal alive today, from the blue whale to the house mouse, from the elephant to the bat hanging in its cave, from the giant panda to the cheetah, owes its existence, in a direct and literal sense, to the end Cretaceous extinction. It was that extinction that cleared the ecological space the mammals needed to become what they are. Without the asteroid, without the non-avian dinosaurs dying, the mammals might have remained small and marginal indefinitely, or might have evolved in entirely different directions, or might have eventually been eclipsed by a new radiation of dinosaur forms. But the asteroid did fall, the non-avian dinosaurs did go extinct, the mammals did inherit the Earth, and here we are. We are the biological consequence of 165 million years of dinosaur rule. Not despite the dinosaurs, but because of them. The world the dinosaurs built, the forests they helped shape, the soils enriched by their bodies, the evolutionary pressures they created on every other organism that shared their world, all of that contributed to making the world in which our ancestors eventually evolved. We are made from the same biological materials the Cretaceous world was made from. We breathe air whose chemical composition was shaped in part by the photosynthesis of Cretaceous plants. The flowers we see, the birds we hear, the insects that pollinate the plants we eat, all of these things trace their lineages back to the Cretaceous world, the world the dinosaurs built. And the dinosaurs themselves, of course, did not entirely disappear. The birds are dinosaurs, not metaphorically, not in some loose evolutionary sense. In the strict technical taxonomic sense, birds are theropod dinosaurs, as dinosaurian in their classification as Tyrannosaurus rex, or Brachiosaurus or Triceratops. The small feathered theropods of the Jurassic and Cretaceous gave rise, through an unbroken chain of ancestor and descendant, to the birds. The hollow bones of a sparrow are the hollow bones of the theropod lineage. The flight feathers of an eagle are the evolution of the simple filamentous feathers first documented in Cretaceous China. The eggs of a chicken are the eggs of a lineage that has been laying eggs without interruption for 200 million years. Every bird you see is a dinosaur. There are approximately 10,000 species of birds alive today. They inhabit every continent, including Antarctica. They have colonized every environment from the deepest oceans, where penguins and diving seabirds pursue fish, into dark, cold water, to the highest mountains, where bar-headed geese cross the Himalayas on migratory routes that require them to breathe air with half the oxygen content of sea level atmosphere. They range in size from the ostrich, nearly 9 feet tall and weighing up to 300 pounds, to the bee hummingbird of Cuba, less than 2.5 inches long, the smallest living bird in the world. By number of species, by geographic range, by ecological diversity, by sheer variety of form and function, the birds are among the most successful groups of large animals on the planet. They are the continuing presence of the dinosaur lineage in the living world, a lineage that began with small bipedal animals in the wet aftermath of the Carnian pluvial episode 234 million years ago, and that continues today, unchanged in its fundamental nature, still flying, still singing, still laying the eggs that are the oldest continuous biological inheritance of the vertebrate world. When you hear a bird singing in the morning, you're hearing the voice of the most ancient surviving animal dynasty on Earth. Now step back far enough to see the whole 165 million years at once. 165 million years. Try to hold that span in your mind as a single thing. If you compressed all of recorded human history, every civilization from ancient Sumer to the present day, into a single day, 165 million years would be equivalent to approximately 9,000 of those days, 25 years of days. If you drove at highway speeds for 165 million years, you could travel a distance greater than the circumference of the observable universe. The dinosaur empire lasted for a length of time that simply exceeds the capacity of human imagination to hold directly. We can state the number, we can make comparisons, but we cannot truly feel it, the way we cannot truly feel the distance to a star. It is too large for direct comprehension. And in all of that time the dinosaurs were there, not as a static presence, not as the same animals doing the same things for 165 million identical years. The dinosaurs of the Triassic would not have recognized the dinosaurs of the Jurassic. The dinosaurs of the Jurassic would not have recognized the dinosaurs of the Cretaceous. The lineage was in constant motion, constantly changing, constantly experimenting, producing new forms and losing old ones, adapting to every world it encountered and shaping every world it inhabited. The Carnian pluvial episode gave them their start. 2 million years of rain that cleared the field of the dominant animals that had been keeping them marginal, and opened the ecological space they needed to begin their extraordinary expansion. The end-Triassic extinction gave them their second push, another catastrophe that eliminated their remaining competitors and left the Jurassic world essentially empty and waiting. The Jurassic Golden Age gave them their greatest scale, sauropods that shook the ground with their passing, predators that towered above the forest canopy, ecosystems of extraordinary productivity and richness. The Cretaceous explosion gave them their greatest diversity, hundreds of species filling every ecological role the terrestrial world could offer, from the apex predators to the insectivores, from the armoured tanks to the swift feathered sprinters, from the giants to the tiny. And then the end, the asteroid and the silence and the emptied world. And then the birds, and then the mammals, and then, eventually, us. We are the heirs of the dinosaur world, not their successors exactly, because the birds, their direct descendants, never went anywhere. But we are the ones who inherited the earth that the non-avian dinosaurs left behind, who evolved in the forest descended from the Cretaceous forests, who breathe the air descended from the Cretaceous atmosphere, who eat the fruits descended from the Cretaceous angiosperms, who share the world with the birds descended from the Cretaceous theropods. Every moment of every day we live inside the legacy of 165 million years. The dinosaurs are not gone, they are everywhere. They are in the robin singing outside your window in the morning, they are in the hawk turning slow circles on the rising thermals above the hills, They are in the deep bone structure of every bird you have ever seen, in the hollow bones and the air sacs and the scaly feet and the eggs laid with the practiced confidence of a 200 million year inheritance. They are in the soil that feeds the plants that feed you, enriched over millions of years by the bodies and the dung and the slow decomposition of the dinosaur world. They are in the amber sitting in a museum drawer somewhere, a perfect bead of ancient resin containing the exquisite preserved body of a Cretaceous insect, a window held open into a world of 66 million years ago. They are in the rock layers that preserve their footprints and their bones and their eggs and sometimes the last impressions of their feathers, library cards stamped with the date of a world that ended before our ancestors were anything more than small, frightened, remarkable mammals hiding from the feet of the very last Cretaceous giants. They are in the deep time that produced them and that produced us, the 4.5 billion years of this planet's patient, creative, endlessly generative history. They are here. They have always been here. And this story, their story, is one of the most magnificent things the living world has ever told. Thank you so much for watching. If you enjoyed this journey through 165 million years of the most extraordinary animal dynasty in Earth's history, please consider leaving a like and subscribing to the channel. It really does help us continue making more content like this, more long journeys through deep time, more stories of ancient worlds and the extraordinary lives that filled them. Anyways, see you in the next one. The story is ending now. Not abruptly, not with a door closing. Just gently, the way a long day finally releases into evening, the way light fades from a sky that has been bright all afternoon, and grows softer and softer until it becomes something warm and dark and quiet. Let the images of the ancient world begin to drift. Let the giant sauropods grow quiet in the deep forests, their enormous bodies settling, their long necks curving down toward the soft ground, their eyes closing. Let the hadrosaur herds slow their movement and find their resting places on the warm Cretaceous floodplains. Let the tyrannosaur lower its massive head. Let the pterosaurs fold their wings against their bodies on their high, rocky perches and look out over a world full of evening light and slow wind. Let the Jurassic forest settle into its nighttime sounds, the insects, the distant calling of early birds in the canopy, the slow, almost geological creak of ancient trees in the wind. Let the Triassic shore grow quiet under the first stars of a world that has never seen a human eye. Let all of it rest. You have travelled an extraordinary distance tonight, further than any spacecraft has gone, deeper than any instrument has measured. You have stood in the forests of the Jurassic and heard the footfalls of the giants. You have watched the first small dinosaurs move through the wet aftermath of the Carnian rains. You have seen the flowers open in the Cretaceous morning and heard the hadrosaurs calling through the ancient trees. You carry that with you now. The deep past is part of you in a way that is real and biological, not merely imagined. You're descended from the world the dinosaurs built. You're made from the same matter that made them. And now it is time to rest. Let your breathing slow. Let your body become heavy and warm and deeply still. Let the images of the ancient world carry you gently down into sleep, the way a river carries a leaf, slowly, peacefully, without effort or resistance. The dinosaurs are at rest. The ancient forests are quiet. The long story of the most magnificent dynasty in the history of land life has been told, and it is beautiful, and it is done for tonight. Sleep now, rest now. You are perfectly safe. The night is quiet and long and gentle. And somewhere outside, in the tree nearest to wherever you're sleeping, a bird is sitting in the dark on a branch, its eyes closed, its feathers ruffled against the night air, breathing slowly. It has been here, in one form or another, for 200 million years. It will be here in the morning. Sleep well. If you could visit any period of the dinosaur era, the Triassic, the Jurassic, or the Cretaceous, which would you choose, and which dinosaur would you most want to see? Leave a comment below. I read every single one, and wherever in the world you are listening from tonight, I hope you sleep deeply and dream of ancient things. The coastal forests of Pangaea deserve more attention than a simple description can give them. To understand what life was like in the early and middle Triassic world, you need to understand what it felt like to stand in one of those forests, because the forests were where almost everything interesting in the terrestrial world was happening. The vast, empty interior of the supercontinent had its own severe beauty, its own geological grandeur, but the forests were where the animals were, where the plants competed and collaborated and evolved their patient strategies for survival, where every resource that complex terrestrial life depended on was concentrated. Imagine standing at the edge of one of those Triassic forests, perhaps on the coast of what would eventually be southern Europe, perhaps 240 million years ago. The forest begins abruptly a few hundred meters from the high water line of the sea, rising out of a narrow band of coastal flats where the tidal zone has deposited its sediment. The first trees you reach are primitive conifers, their trunks straight and relatively slim compared to the great conifers of the Jurassic that would follow them, their branches arranged in whorls along the trunk, each whorl carrying a ring of stiff, outward-pointing branches that hold their needle-like leaves at angles designed to catch the maximum available light. Beneath the conifers, and in any clearing where the tree canopy has been broken by storm or flood, or the natural death of an old tree, the ferns are extraordinary. Not just ground ferns, though those are everywhere, their fronds unrolling in the damp shade and spreading wide to catch the diffuse green light filtered down through the canopy above. Tree ferns as well, their slender trunks reaching 15 or 20 feet before expanding into canopies of arching fronds, their surfaces spotted with the dark patches of spore cases on the underside of each frond. In the wet season, when the coastal monsoons come, these ferns grow with a speed that is visible, not metaphorically but literally, the new fronds uncurling at the tips of each branch with a pace that can be measured day by day. The cicads stand among the ferns with a stiff, architectural formality. They look ancient because they are ancient, their basic body plan almost unchanged for hundreds of millions of years, their rosette of stiff palm-like leaves emerging from a squat, barrel-shaped trunk that grows so slowly it might add an inch per year in a good season. Some of the larger cycads in this forest have trunks 5 or 6 feet across, which means they have been growing for centuries or possibly millennia. They carry their reproductive structures in large central cones, thick and heavy at the centre of the leaf rosette, releasing their pollen on the wind and receiving the pollen of others with a passive wind-blown system that works well enough but that will, in another 100 million years, be comprehensively outcompeted by the flowering plants and their more efficient animal-assisted pollination strategies. The sounds of this forest are different from any modern forest sounds. There are no flowering plants here, so there are no bees, no butterflies, none of the high-pitched buzzing and fluttering of the pollinator world that fills modern forests with their characteristic summer acoustic texture. The insect sounds that do exist are lower in register, the rasping of primitive crickets, the drone of beetles flying between the cycad cones, the softer rustling of small arthropods moving through the leaf litter. There are no birds, no singing, no territorial calls, no alarm notes, none of the layered avian soundscape that characterizes modern forests worldwide. What there is instead is a kind of deep, ambient life noise. The wind in the conifer needles, a sound slightly different from the wind in broadleaf trees, drier and more rustling, less the wash and sigh of broad flat leaves, and more a continuous whisper of thin stiff needles. The sound of water, always, in this coastal forest. The drip from leaf to leaf after rain. The distant sound of the river making its way through the forest, a few hundred meters inland. The soft lapping of the sea at the far edge of the trees. The occasional crack of a branch. The rustle and thud of a fallen tree that has been rotting for decades finally giving way under the combined weight of the fungus consuming it from within, and the small animals using its crumbling wood for shelter. And moving through it all, the animals. The small synapsids that inhabit this forest are diverse and in their own way remarkable. Some of the cynodonts, the most mammal-like of the synapsids, are very small, barely larger than modern mice, and they move through the undergrowth with quick, nervous energy. Their large eyes adapted for low-light conditions, their sensitive whiskers helping them navigate the complex three-dimensional environment of the forest floor. They eat insects primarily, which are abundant in the warm, humid conditions of the coastal forest. They eat seeds and small fruits when they can find them. They eat smaller animals when the opportunity presents. Some cynodonts are larger, approaching the size of modern cats or small dogs, and these are the predators of the smaller synapsids, hunting through the undergrowth with a slightly slower, more deliberate quality, using smell as much as sight to locate their prey. Their teeth are differentiated, not as thoroughly as in true mammals, but enough that you can see the direction evolution is moving. Incisors for biting, a larger canine tooth for gripping, and some teeth further back beginning to show the cusped surfaces that characterize molar teeth adapted for complex chewing. The large synapsids of this forest are perhaps the most alien of all. The dicynodonts, bulky barrel-bodied herbivores that had survived the Great Dying against all reasonable expectations, still persisted in some regions of the early Triassic, though their diversity had been catastrophically reduced. They moved slowly and heavily, their broad feet leaving deep impressions in the soft forest soil, their beaked mouths cutting through the ferns and horsetails that formed their primary diet. They were stolid animals, seemingly built for endurance rather than agility. Their thick hides and massive digestive systems optimized for processing large volumes of fibrous, low-quality plant material. Among all of these animals, moving through the same forest, sharing the same resources, living in a web of predation and competition and symbiosis with all the other inhabitants of the Triassic coastal world, were the archosaurs. The early archosaurs of the Triassic were diverse and interesting, and understanding them helps us understand the context in which the dinosaurs first appeared. The word archosaur translates roughly as ruling lizard, though this is somewhat misleading because archosaurs were not lizards in any modern technical sense. They were a distinct evolutionary lineage that split from the main reptile line during the Permian or very early Triassic, and by the time of the Middle Triassic they had diversified into several distinct groups following several distinct evolutionary paths. One group of archosaurs gave rise to the crocodilian lineage. These early proto-crocodilians were not yet the semi-aquatic ambush hunters we recognize today. Many were terrestrial, moving on long, relatively upright legs through the forest understory. Some were bipedal, some were small and quick. But they carried in their genetic inheritance the basic body plan and the physiological toolkit that would eventually, after the end-Triassic extinction and the ecological restructuring of the early Jurassic, lead them back to the water and into the extraordinary evolutionary success story of the modern crocodilians. A second group of archosaurs gave rise to the pterosaurs, the flying vertebrates. The conquest of air by a group of animals that had been purely terrestrial is one of the most dramatic evolutionary transitions in the history of vertebrate life, and it happened during the Triassic, in this period we are describing, in the forests and open grounds and coastal cliffs of Pangaea. The first pterosaurs appear in the fossil record in the late Triassic, and by the time they appear they are already clearly adapted for flight. Their wing membranes already developed, their bones already hollow and lightened, already in possession of the basic functional architecture of the pterosaur flight system. The third archosaur group, the one most relevant to our story, gave rise to the dinosaurs. Understanding what made the dinosaur lineage distinct from other archosaurs, what combination of anatomical and physiological features set the dinosaurs apart and ultimately gave them the tools they needed to inherit the world, requires looking carefully at what we know about their skeletons, their posture, their movement, and their physiology. The ankle joint is important here, in a way that might seem surprising for a discussion of the most spectacular animals in Earth's history. The ankle joint of an archosaur is a diagnostic feature, meaning it helps identify which archosaur group an animal belonged to. The dinosaur ankle was what paleontologists call a mesotarsal ankle, with a distinctive hinge-like structure that allowed the foot to flex primarily in a single plane, the plane of forward motion. This is the same basic ankle architecture found in modern birds, the living dinosaurs. It is different from the ankle architecture of crocodilians and different from the ankles of most other Triassic archosaurs. This seemingly small anatomical detail had significant functional consequences. The mesotarsal ankle, combined with the upright parasagittal posture of the dinosaur leg, produced a locomotor system of considerable efficiency. It was a body plan built for moving forward, for sustained locomotion, for covering ground efficiently over long distances. In the open, variable, wet and transformed landscape of the post-Carnian Triassic world, where animals needed to move through diverse and challenging terrain, and where the old territorial boundaries maintained by the large Rauisuchians were collapsing, this efficient locomotor system was a genuine competitive advantage. The hip socket is also distinctive. In the earliest dinosaurs, the hip socket had a hole in the centre of the acetabulum, the cup into which the femur, the thigh bone, fits. In most other reptiles, including most other archosaurs, The acetabulum is a solid cup. In dinosaurs, it is open in the centre. This open acetabulum, combined with the interned femoral head that fits into it, allowed for a more fully erect posture, the limbs swinging in a plane close to vertical rather than canted outward at all. It was a more complete, more mechanically efficient upright stance than any other group of large reptiles had achieved. These are the small technical details that, combined with whatever advantages the early dinosaurs had in metabolism and respiratory efficiency, added up to a competitive edge that was invisible in a stable world, but became decisive when the world changed around them. In the middle Triassic forests and floodplains of Pangaea, the early dinosaurs were accumulating advantages. Generation by generation, variation by variation, ancestor by descendant, the dinosaur lineage was becoming something that the world was about to need. The Triassic world moved through its seasons without hurry. The monsoons came and the monsoons went. The synapsids lived and died. The Rauisuchians patrolled their territories. The rhynchosaurs grazed in their thousands. The cycads grew their slow inches. The rivers flooded and receded and flooded again. And the small bipedal things in the margins of the forest kept living, kept adapting, kept accumulating the quiet advantages that would one day make them the rulers of the earth. The transformation of the continental interior during the Carnian pluvial episode was not merely a matter of more rain. It was a complete restructuring of how the land related to water, and the consequences of that restructuring touched every organism that lived anywhere on the surface of Pangaea. Before the rains came, the interior of the supercontinent had been characterized by what geologists call an Aeolian regime. Aeolian comes from Aeolus, the Greek god of winds, and an Aeolian environment is one shaped primarily by wind rather than water. The great red deserts of the Triassic interior were classic Aeolian environments. Vast fields of wind-sculpted sand dunes, broad gravel plains where the wind had stripped away the fine particles and left only the larger stones too heavy to be moved. Rare temporary lakes that formed in topographic depressions during the brief, violent coastal monsoon season, and then evaporated within months. The rock that formed in these environments, the red sandstones and siltstones that make up so much of the Triassic geological record before the Carnian pluvial episode, bears all the signatures of an Aeolian world. Cross-bedded sand layers laid down by migrating dunes, wind-polished grains, oxidized red iron staining that develops only when sediment is exposed to air and drying rather than being deposited under water. Then the rains began. And as they intensified, as year after year brought more rainfall and the dry season shortened, and the wet seasons lengthened and deepened, the Aeolian world began to be replaced by a fluvial world, a world shaped by water. The first water to arrive in significant quantities in the interior would have found a landscape completely unprepared for it. Aeolian soils have no structure of the kind that forest soils develop. They have no root networks holding particles together, no accumulation of organic matter binding the mineral grains, no biological crust of algae and fungi that in living desert soils provides at least some resistance to erosion. They are loose, unconsolidated, ready to be picked up and carried by the first energetic flow that encounters them. The initial rains therefore produced extraordinary erosion. The water arrived in the interior as it always had, as flash flood pulses from the coastal monsoon systems, but the floods were now larger, more frequent and longer lasting than anything the interior landscape had experienced. The loose red sand and silt was scoured from the slopes and the plains and carried downslope in brown, turbid flows that spread across every flat surface and deposited their loads wherever the flow slowed enough to let the particles settle. The sedimentary geology of the Carnian pluvial episode records this process in extraordinary detail. You can see it in the rock if you know what you're looking at. The transition from Aeolian red beds to fluvial grey beds is not always gradual. In some sections, it is almost abrupt, a sharp boundary between the ordered cross-bedding of wind-deposited sand and the chaotic, poorly sorted sediments of a flash flood deposit. The transition marks, in the rock, exactly the day, within the resolution of geological dating methods when the balance tipped, when the rains became heavy enough and sustained enough to dominate over the wind in shaping the landscape. Above that boundary, the story told by the rocks changes. River channel deposits appear. You can recognize ancient river channels in the rock record by their distinctive shape and their internal sedimentary structure. They are lens-shaped bodies of coarser sediment, sand and gravel and sometimes cobbles, cutting through finer-grained floodplain deposits. Inside the channel deposits, the sand grains are sorted by size, the heaviest concentrated at the base, lighter grains above, the whole arrangement reflecting the hydraulic sorting of flowing water carrying a mixed sediment load. Lake deposits appear. Ancient lake sediments have their own distinctive character. They are fine-grained, the particles small because the still or slow-moving water of a lake only has energy to transport and deposit the finest particles. They are often laminated, thin, alternating layers of slightly different compositions, reflecting seasonal changes in input or productivity. Sometimes they contain the fossils of organisms that lived in the lake, preserved in the fine sediment with a fidelity that Aeolian deposits rarely achieve. Coal deposits appear. Coal forms from accumulated plant material, usually in swampy, water-saturated environments, where dead vegetation builds up faster than it can be fully decomposed. The presence of Carnian-age coal in regions that had previously been desert is one of the most striking pieces of evidence for the magnitude of the rainfall increase. You cannot make coal in a desert. You need sustained wet conditions and abundant plant growth. The Carnian coal deposits tell us, unambiguously, that the interior of Pangaea had been transformed from one of the driest environments on Earth to one of the wettest. The chemistry of the rocks tells the story as well. Geochemists studying the Carnian pluvial episode have analysed carbon and oxygen isotopes preserved in ancient soils and carbonate deposits, and the signatures they find match precisely what would be expected from a period of dramatically elevated atmospheric carbon dioxide and significantly increased rainfall. Carbon isotope ratios shift at the boundary of the Carnian pluvial episode, reflecting the massive injection of volcanic carbon dioxide from the Rangelia eruptions. Oxygen isotopes in ancient pedogenic carbonates, minerals that form in soils and record the temperature and rainfall conditions at the time of their formation, indicate both warming and dramatic increases in precipitation. The sulfur isotopes in the rocks tell their own story. Sulfur is cycled through the environment by both biological and geological processes, and the isotopic ratios recorded in ancient rocks can distinguish between different sources and pathways. During the Carnian pluvial episode, sulfur isotope signatures change in ways consistent with increased weathering of sulfur-bearing rocks, which happens when large volumes of water flow across the landscape and dissolve and transport chemical elements from the rock. You need a lot of water, flowing for a long time, to produce the kind of sulfur isotope shift recorded in Carnian-age deposits. All of these lines of evidence, the sedimentary structures, the rock colours, the chemical signatures, the fossils preserved within the layers, converge on the same conclusion. Something happened to Earth's climate during the Carnian stage of the Triassic that was global in scale, profound in magnitude, and prolonged beyond anything in the living world's experience. The living world's response to this transformation was varied and complex, and it played out differently in different places and in different groups of organisms. In the plant world, the transformation was one of the most comprehensive in the history of terrestrial vegetation. The seed ferns that had dominated so much of the Triassic plant world were, as we have noted, casualties of the persistent wetness. Their decline created enormous amounts of ecological space in the plant community, space that needed to be filled by something else. The organisms that filled it were the conifers, or more precisely the new, more advanced conifer families that were diversifying during the Carnian pluvial episode, in ways that took advantage of the increased moisture rather than being destroyed by it. Modern conifer families, the ones whose descendants we recognize today, pines and spruces and firs and redwoods and their many relatives, trace their origins to radiations that happened during and immediately after the Carnian pluvial episode. The fossil record of conifers from this period shows a diversification that mirrors the diversification of the dinosaurs in its pace and in its geographic spread. New genera, new species, new forms adapted to different moisture regimes and different soil types and different elevations, all appearing within the same geologically brief window that marks the transformation of the climate. These Carnian conifers were not the stunted, moisture-stressed trees of the early Triassic. They were large, productive organisms growing in soils that were, for the first time, reliably and abundantly watered. Some of them grew to significant heights, their root systems penetrating the newly saturated soils and their crowns spreading to capture the diffuse light that filtered through the omnipresent cloud cover of the wet period. They produced cones in abundance. They produced resin in abundance, and that resin sometimes entrapped insects and other small organisms and slowly hardened into amber, those extraordinary time capsules that today preserve carnian insects with a fidelity that stone cannot match. The expansion of the conifers was not merely a botanical event, it was the foundation of a new ecosystem. Dense conifer forests, covering regions that had been desert for millions of years, created entirely new habitats for animals. The forest floor, shaded and humid and deep with accumulating organic material, was a habitat without precedent in the continental interior. The canopy, full of insects and the seeds and pollen and other resources that large forest ecosystems always generate, was another new dimension of available ecological space. The rivers flowing through the expanding forests were bordered by riparian zones, narrow strips of especially dense and productive vegetation that served as corridors for animal movement from the coast into the interior. Animals followed the spreading forests inward. Fish, which in the Precambrian world could only penetrate the interior along the few seasonal river courses that reached that far, suddenly had access to an enormous network of permanent rivers and lakes. New fish species evolved to fill the new freshwater habitats. Some ancestral lineages of the ray-finned fishes, which would eventually become the most diverse group of vertebrates on Earth, appear in the fossil record of the Carnian pluvial episode, precisely because the new freshwater environments they needed to diversify into had not previously existed. Amphibians, which require water for reproduction, suddenly found themselves in a world where water was everywhere. Amphibian fossils from the Carnian pluvial episode show diversification in groups that had previously been limited to the narrow coastal zones where water was available year-round. Some of these newly aquatic and semi-aquatic amphibians were substantial animals, apex predators in the new freshwater ecosystems, large-bodied hunters that pursued fish and other vertebrates through the warm, dark rivers and lakes of the transformed interior. And following the fish and amphibians, following the spreading forests and the new food chains they supported, came the first tentative movement of the small, quick, bipedal dinosaurs into the continental interior. This was a movement of immense long-term significance. The continental interior of Pangaea had been, for hundreds of millions of years, essentially unavailable to complex terrestrial life because it was too dry. The Carnian pluvial episode, by creating a network of rivers and forests that extended from the coasts into the deep interior, opened that vast space to colonization for the first time. The animals that took advantage of that opportunity gained access to a territory the size of multiple modern continents, rich with resources, unoccupied by established competitor populations, essentially empty and waiting. The dinosaurs were among those that moved inward. Their fossil record during and after the Carnian pluvial episode shows them appearing in geological formations from increasingly inland locations, following the spreading river systems, exploiting the new forests, adapting to the varied conditions they encountered as they moved from the coast into the heart of the transformed supercontinent. This inland expansion was part of what made the post-Carnian radiation of the dinosaurs so comprehensive. They were not simply inheriting the coastal world that the Rauisuchians and Etosaurs had occupied. They were claiming a world that had never been properly claimed before. The whole interior of the supercontinent, newly watered and newly forested and newly accessible, was theirs to fill. And fill it they would. The 2 million years of the Carnian pluvial episode were not simply a period of killing and replacement, though they were that too. They were a period of opening, a geological event that unlocked resources and spaces and possibilities that had been physically unavailable to complex terrestrial life for the entire history of Pangaea. The rain was not just destroying the old world, it was creating a new one vastly larger than what had existed before. The dinosaurs were the ones who walked into it. The anatomy of the earliest dinosaurs repays careful attention because it was that anatomy, those specific body features inherited from a common ancestor and then refined and modified through tens of millions of years of evolution, that made everything the dinosaurs eventually achieved possible. Let us look carefully at what an early dinosaur actually was. Start with the neck. Dinosaur necks were, from the very beginning of the lineage, longer relative to body size than those of most other reptiles. This was not an accident or an evolutionary quirk. It was a functional advantage. A longer neck means a larger feeding radius from any given body position. An animal that can swing its neck through a wide arc while keeping its body stationary can effectively sample a much larger volume of the environment for food than an animal that must move its entire body to access the same range. This feeding advantage was small in the earliest dinosaurs, where neck elongation was modest. But it was the beginning of a trajectory that would eventually, in the Jurassic sauropods, produce necks 40 or 50 feet long and feeding radii completely without parallel in the history of land life. The teeth of early dinosaurs were varied in a way that reflects the dietary flexibility we have already noted. Some early dinosaurs had teeth that were more leaf-shaped and serrated, suggesting a mixed diet that included plant material. Others had teeth that were more blade-like and recurved, designed for seizing and holding prey. The variation among individuals in dental morphology is greater than in more specialized later forms, consistent with the interpretation that the earliest dinosaurs were occupying a broad ecological role rather than a narrow specialized one. They were, in the language of ecology, generalists, and generalists are survivors in ways that specialists are not. The hand of an early dinosaur is another revealing structure. Most early dinosaurs had 5-fingered hands, though the 5th finger was often reduced to a small vestigial structure, and the 4th was also reduced. The first 3 fingers were well developed, each tipped with a curved claw. The hand could pronate and supinate to some degree, meaning it could be turned palm down or palm up, giving it a range of motion that allowed grasping. This was a hand that could hold, that could manipulate, that could seize struggling prey and maintain grip. The hands of later large theropods, like Tyrannosaurus rex, would reduce dramatically in relative size, but in the earliest dinosaurs the 3-fingered grasping hand was a functional tool, part of the predatory toolkit of an agile opportunist. The eye orbit in early dinosaur skulls is relatively large, suggesting large eyes. Large eyes in an animal's skull generally indicate one of 2 things: adaptation for low-light activity, or adaptation for visual acuity and high detail, or both. The inference that at least some early dinosaurs were capable of activity in low-light conditions, potentially crepuscular, active at dawn and dusk or even partly nocturnal, has implications for their ecological position. An animal that can hunt or forage in low light has access to time periods when cold-blooded competitors are metabolically slowed and less active. This temporal niche, the low-light hours, would have been another dimension of the competitive space that the early dinosaurs were quietly claiming. The tail of an early dinosaur was long and muscular, serving primarily as a counterbalance to the weight of the head and neck and body when the animal was moving bipedally. This counterbalancing function of the dinosaur tail is fundamental to the biomechanics of bipedal locomotion, and it constrained tail anatomy in ways that remained consistent throughout the lineage's history. You cannot have a long neck on a biped without a long tail to balance it, which is why even the earliest, most modest dinosaurs already carried the basic proportional scheme of head-neck-body-tail that would be refined and elaborated throughout the next 165 million years. The feet of the early dinosaurs show the beginning of features that would become definitive of the group. They walked on the digits, on the toes, rather than on the flat of the foot. This digitigrade locomotion, which we share with running animals like dogs and cats and which birds still practice because they are dinosaurs, raises the effective leg length by extending the foot into the lower limb. It provides more spring and more power in each stride. It is energetically superior to plantigrade locomotion, walking flat-footed the way we do for sustained running. Early dinosaurs were already configured for speed in this fundamental way. The bones themselves, the internal structure of the bone tissue visible in cross-section under a microscope, tell stories about growth and metabolism. The bone microstructure of early dinosaurs generally shows patterns consistent with fast, sustained growth, the kind of growth seen in modern warm-blooded animals that devote large amounts of metabolic energy to growing rapidly to adult size. This is in contrast to the slower, more seasonal growth typical of modern cold-blooded reptiles. Fast growth implies a high metabolic rate. A high metabolic rate implies endothermy, the generation of body heat internally. The bone tissue of the earliest dinosaurs is already, tentatively, suggesting that these were not cold-blooded animals in the modern crocodile or lizard sense. All of these features, the long neck, the flexible grasping hand, the large eyes, the counterbalancing tail, the digitigrade foot, the fast-growth bone tissue combined with the upright posture and the probable respiratory air sac system produced an animal of genuine and underappreciated sophistication. Not a primitive, simple reptile with a few accidental advantages. A coherent, well-integrated biological system that was, when measured against the challenges of the changing Triassic world, extraordinarily well-equipped. The early dinosaurs found their world in the aftermath of the Carnian pluvial episode not through conquest but through compatibility. The world that had emerged from 2 million years of rain was a world that matched them, a world whose challenges aligned with their particular collection of capabilities, a world that was, in the deep biological sense of the word, theirs. The fossil sites of the late Triassic give us glimpses of this early dinosaur world that are precious in their rarity and detail. The Ischigualasto Formation of northwestern Argentina, formed in a river basin environment approximately 231 to 227 million years ago, is one of the most important dinosaur-bearing formations in the world. Its rocks preserve not just Eoraptor and Erarosaurus, but an entire community of animals, a snapshot of a late Triassic ecosystem at one of the most critical moments in vertebrate evolutionary history. Alongside the early dinosaurs, the Ischigualasto preserves early cynodont mammals, early rhynchosaur herbivores, early etiosaurs, and various other archosaurs. It is a community in transition, showing the mixture of old and new that characterizes the period of the dinosaurs' rise. The Chinle Formation of the American Southwest, deposited roughly 230 to 220 million years ago, preserves another critical window into the late Triassic world. This formation, which includes the famous Painted Desert and Petrified Forest National Park, contains an extraordinary array of fossil wood, fossilized logs of ancient conifers sometimes 60 or more feet long, preserved in silica and now exposed in the desert landscape as though the trees fell yesterday rather than 200 million years ago. The Chinle also contains abundant fossil animals, including the early theropod dinosaur Coelophysis, early crocodilians, and various other archosaurs and synapsids. Walking through Petrified Forest National Park today is a strange and moving experience. You're walking through a forest that exists in stone, a forest that grew while the first dinosaurs were learning to inherit the world, preserved in extraordinary detail by a volcanic ashfall that buried the logs and the silica-rich groundwater that slowly replaced the organic wood with mineral crystite. The trees are heavy and beautiful, their bark patterns and growth rings still visible after 200 million years, their wood now the colours of mineral, purple and red and orange and cream. In the same formation as those petrified trees, the Coelophysis herds moved. The small, fast, hollow-boned theropods that would be among the first dinosaurs to establish themselves as numerically dominant in a terrestrial ecosystem. They were not giants. They would never be giants. But they were successful, genuinely and increasingly successful, in a way that their ancestors in the mid-Triassic margins could never have been. The world had changed to fit them. And the world would keep changing and they would keep fitting. The story of the dinosaurs' rise is not a story of a single decisive moment. It is not a story of sudden dominance achieved through some spectacular evolutionary breakthrough. It is a story of patient accumulation, of slow ecological colonization, of the quiet compounding of small advantages in a world that kept, catastrophe by catastrophe, clearing away the obstacles between the dinosaurs and their destiny. And that destiny, that extraordinary 165 million years of dominance, was still just beginning. The world that emerged on the other side of the end-Triassic extinction was profoundly different from the world that had entered it, and the differences were not merely cosmetic. The ecological architecture of the terrestrial world had been fundamentally restructured, and the restructuring created conditions that, for the dinosaurs, amounted to something close to an open invitation. Consider the herbivore niches. In the mid-Triassic world, the large herbivore roles were occupied by rhynchosaurs, by dicynodonts, by etosaurs, by large herbivorous synapsids of various kinds. These were animals with millions of years of evolutionary history behind them, populations established across the landscape, dietary preferences and body plans refined through countless generations of selection. They were not going to yield their ecological positions easily, and they did not. While the Carnian pluvial episode had weakened them, it had not entirely displaced them. Some rhynchosaur populations persisted into the latest Triassic. Some large synapsid herbivores continued to occupy their niches. The end-Triassic extinction changed all of that. When the camp eruptions had done their work, the rhynchosaurs were gone. The large snapsid herbivores were reduced to tiny remnant populations, functionally irrelevant to the ecology of the terrestrial world. The etosaurs were extinct. Every large herbivore niche on the planet was, in ecological terms, empty. And into those empty niches, the prosauropod dinosaurs began to move. The prosauropods were the early members of the sauropodomorph lineage, the branch of the dinosaur family tree that would eventually give rise to the great sauropods of the Jurassic. In the late Triassic and earliest Jurassic, the prosauropods were the largest herbivorous dinosaurs, and in many ecosystems they rapidly became the largest herbivores of any kind. Plesiosaurus, which we have already mentioned, was reaching 30 feet in length. Similar animals were appearing on every continent that had been part of Pangaea, Massospondylus in what is now southern Africa, Lufengosaurus in what is now China, Ankylosaurus in what is now eastern North America. These animals were filling the largest herbivore niche in a way that had never been done before by the dinosaur lineage. And with that filling came ecological significance that the early dinosaurs had never possessed. An animal that is the largest herbivore in its ecosystem is not a marginal player. It is a foundational one. Its feeding behavior shapes the vegetation. Its movement patterns create trails and clearings. Its dung fertilizes the soil. Its carcasses provide resources for a wide range of scavengers and decomposers. Being the largest herbivore means being integrated into the ecosystem in a fundamental way, part of the basic functioning of the system, rather than just a component that could be removed without major consequence. The theropod dinosaurs, filling the predator niches, underwent a similarly comprehensive expansion. In the immediate post-extinction world of the earliest Jurassic, the dominant predators were relatively small theropods, quick and agile, filling the niche vacated by the extinct Rauisuchians. But the diversification was rapid. Within the first few million years of the Jurassic, theropods ranging from small insectivores to mid-sized predators were established across the landscape. And as the prosauropods grew larger, as the large herbivore niches were filled by increasingly massive animals, the selection pressure for large predators grew accordingly. The predator-prey arms race that would ultimately produce Tyrannosaurus rex and the enormous sauropods of the Jurassic had its roots in this early Jurassic world, in the ecological dynamic between expanding prosauropod herbivores and expanding theropod predators, each lineage pushing the other toward new extremes. It is worth pausing to appreciate how remarkable this dynamic is in the long sweep of evolutionary history. The dinosaur empire, that extraordinary 165 million years of dominance, was built on a foundation of competitive release. The dinosaurs did not achieve dominance by outcompeting the animals that had held the large animal niches before them. They achieved dominance because those animals were eliminated twice by geological catastrophes that had nothing specifically to do with the dinosaurs' competitive abilities. The Great Dying had weakened the synapsid dominance that preceded the Triassic. The Carnian pluvial episode had weakened the Rauisuchians and their Triassic contemporaries. The end-Triassic extinction had finished the job. At no point did the dinosaurs defeat their predecessors in direct ecological competition. At every point, the predecessors were eliminated by external forces, and the dinosaurs were the beneficiaries. This is not to diminish the dinosaurs. They were genuinely remarkable animals. Their adaptations were genuinely superior for the conditions of the Jurassic and Cretaceous worlds. The fact that they dominated for 165 million years is evidence not just of their competitive release at the beginning, but of their genuine ecological excellence throughout. Competitive release gets you a seat at the table. Holding it for 165 million years requires real capability. But the origin story matters because it tells us something important about how evolutionary dominance works. It rarely comes through direct head-to-head competition. It usually comes through surviving catastrophes that others cannot survive. Through being, at the moment when the world empties and the niches open, the ones still standing. The dinosaurs were the ones still standing after the Triassic. And they were about to show the world what they could do with that opportunity. The earliest Jurassic world was a world in recovery from extinction, and recovery from extinction has its own particular ecological character. The food webs are simpler than before, the diversity is reduced, the niches are not all filled, and the filling of them produces a dynamic quality to the ecosystem, a sense of things still settling into place, still being worked out, still finding their configurations. In that dynamic, settling world, the dinosaurs were extraordinarily active. New species were appearing at a pace that, while not as fast as some later radiations, was genuinely rapid in geological terms. New body sizes were being explored. New dietary strategies were being tested. The ecological possibilities of the dinosaur body plan were being worked through systematically by the blind, patient process of variation and selection, generation by generation, in ecosystem after ecosystem. The result, by the Middle Jurassic, was a world that was becoming recognisably dinosaurian, a world in which dinosaurs occupied the large predator niche and the large herbivore niche, and many of the medium-sized niches in between. A world in which the non-dinosaur components of the ecosystem, the early mammals and the crocodilians and the pterosaurs and the fish and the invertebrates, were all present and important, but were organised around and partly defined by the dinosaur communities they shared their world with. The Golden Age was coming. The Jurassic was coming. And it would be extraordinary. The sauropods deserve more than a single description, because they were not a single thing. They were a lineage, a dynasty within a dynasty, and across the 100 million years or so of their existence, they produced forms so varied, so extreme, so apparently boundless in their evolutionary creativity, that trying to describe them with a single set of adjectives is like trying to describe all of human architecture by describing one building. Let us spend some time in the Jurassic moving through the different habitats and meeting the different forms. Start in the late Jurassic lowland forests of North America, in what is now Wyoming or Utah or Colorado, perhaps 150 million years ago. This is the world of the Morrison Formation, one of the most fossil-rich geological units in the world, a broad expanse of ancient floodplain and river channel and lake deposits that preserves an ecosystem of extraordinary richness. The Morrison world was warm and seasonally varied, with wet seasons that flooded the great river systems and dry seasons that concentrated the animals at the remaining water sources. The vegetation was dominated by tall conifers and cycads and tree ferns, with a dense understory of ground ferns and horsetails along every waterway. The landscape was flat or gently rolling, divided by the broad meandering rivers into distinct ecological zones, each with its own characteristic community of plants and animals. The sauropods of the Morrison were diverse. Brachiosaurus, the tall giraffe-like browser we have already met, shared this ecosystem with several quite different sauropod designs. Diplodocus, the horizontal long-tailed sweeper. Apatosaurus, once called Brontosaurus, massively built and deep-bodied with a neck held roughly horizontally, adapted for sweeping broad swathes of low vegetation with lateral neck movements. Camarasaurus, shorter-necked and heavier built than Diplodocus, with spoon-shaped teeth that could handle tougher vegetation. Supersaurus, one of the longest dinosaurs ever known, possibly reaching 110 feet from nose to tail tip. These different sauropods were not simply size variants of the same design, they were functional specialists, each adapted to exploit a different fraction of the enormous plant resources available in the Morrison ecosystem. Brachiosaurus reached high into the canopy that others could not access. Diplodocus swept the mid and low levels. Camarasaurus processed tougher vegetation that the leaf-stripping specialists left behind. They partitioned the plant resources among them, not through any conscious strategy, but through the evolutionary process of character displacement, where species in the same community tend to diverge in their resource use to avoid direct competition. This partitioning of resources among multiple large herbivore species is something the Jurassic world achieved on a scale never seen before or since. The sheer biomass of sauropod plant consumption in a Morrison Formation ecosystem must have been extraordinary. These were animals requiring hundreds of pounds of vegetation per day. A large herd of sauropods moving through a forest was not a benign presence. It was an ecological force, shaping the vegetation by its consumption, creating clearings where old trees had been knocked over or stripped, maintaining the open ground that some plant species and many smaller animals depended on. The predators of the Morrison kept pace with their prey. Allosaurus, the dominant large predator we have already described, was not the only theropod in this ecosystem. Ceratosaurus, named for the small horn on its snout, was a mid-sized predator reaching perhaps 20 feet in length, probably hunting smaller prey than Allosaurus pursued, though their diets may have overlapped substantially. Torvosaurus, a massive predator approaching the size of Allosaurus and known from slightly earlier deposits, may have competed with Allosaurus for the apex predator role. Coelurus and Ornitholestes were much smaller theropods, fast and agile, hunting the small animals, lizards, small synapsids, possibly early birds and pterosaurs that shared the ecosystem's lower trophic levels. The dinosaur community of the Morrison was not simply predators and prey, it was a complete ecosystem. Stegosaurs were common. Multiple stegosaur species have been recovered from Morrison deposits, each with somewhat different plate and spike arrangements, each probably occupying a slightly different ecological niche within the large herbivore category. Dryosaurus was a medium-sized ornithopod dinosaur, bipedal and agile, probably a browser of medium-height vegetation, fast enough to escape predators when necessary. Camptosaurus was a larger ornithopod, reaching 15 or 20 feet in length, capable of both bipedal and quadrupedal locomotion, browsing on low and medium-height vegetation. And then there were the pterosaurs, the crocodilians, the turtles, the lizards, the mammals, the fish, the amphibians, the invertebrates, all the other components of the Morrison ecosystem that provided the ecological context within which the great dinosaurs lived. The crocodilians of the Jurassic were diverse and interesting. Some were the aquatic ambush hunters we recognize from modern rivers. Others were more terrestrial, with long legs and more upright postures than modern crocodilians, moving through the forest understory as active predators. Some were small, hunting insects and other invertebrates. Others were substantial predators, competing with the mid-sized theropods for prey in the river margins and floodplain environments. The Jurassic mammals were still small, still mostly nocturnal, still keeping their heads down while the giants moved overhead. But they were more diverse than they had been in the early Jurassic. Multiple mammal lineages were present in Morrison-equivalent deposits, representing early members of the monotreme lineage, early members of the Therian lineage that would eventually produce the marsupials and placentals, and various other mammalian experiments that left no modern descendants. They filled the small-bodied insectivore and omnivore niches with a thoroughness that prepared them, though none of them could know it, for the explosive radiation that would follow the end Cretaceous extinction. The Jurassic world in other parts of the world was equally rich, differently configured. In what is now Portugal and Tanzania, sauropod faunas broadly similar to the Morrison ecosystem, but with their own distinctive species compositions told the story of the fragmenting Pangaea, producing regional variations on the sauropod theme. In what is now China, a different cast of characters occupied equivalent ecological roles, early members of lineages that would diversify extensively in the subsequent Cretaceous. The Jurassic oceans, bordered by the fragmenting pieces of the ancient supercontinent, were full of their own extraordinary life. Ichthyosaurs, those dolphin-shaped marine reptiles that had been present since the Triassic, were at the height of their diversity. Some Jurassic ichthyosaur species reached enormous sizes, 30 feet and more, their streamlined bodies perfectly adapted for pursuit of the large fish and cephalopods that filled the warm Jurassic seas. Plesiosaurs, those long-necked or large-headed marine reptiles that would eventually inspire the Loch Ness Monster legend, were diversifying rapidly, some evolving extremely long necks with small heads for fish catching, others evolving large heads with powerful jaws for subduing large prey. The Jurassic seas were also full of marine crocodilians, forms that had returned to the water from terrestrial ancestors and developed various adaptations for aquatic life. Some had fish-like tails and flipper-like limbs. Some retained more terrestrial proportions but were clearly capable swimmers. They filled the mid-level predator niches in the marine food web, hunting the abundant fish and smaller marine reptiles in the shallow coastal waters. Above the seas and the forests, the pterosaurs were reaching the beginning of their greatest radiation. New forms were evolving, new sizes were being explored. The basic pterosaur body plan, already extraordinary in its departure from any previous vertebrate design, was being stretched and modified in dozens of new directions by the evolutionary experimentation of the Jurassic period. The Jurassic world, from the deep ocean abysses to the highest conifer canopies to the open skies where the pterosaurs soared on the warm updrafts from the sun-warmed land, was alive with a richness and a complexity that the pre-dinosaur world had never approached. And the dinosaurs were at the centre of all of it. They were not a single kind of animal. They were an empire of forms, a dynasty of diversity, a lineage that had taken the basic body plan bequeathed by those first small Triassic opportunists and expanded it, generation by generation, into everything the terrestrial world could contain. breathe slowly in the Jurassic air, rich with the resin of ancient conifers, warm with the afternoon heat radiating from the floodplain mud. Listen to the deep, irregular rhythm of the sauropod footfalls in the middle distance, and the higher, faster sounds of the smaller dinosaurs moving through the undergrowth. Let it all settle around you, this ancient and magnificent world. You're perfectly safe here. Everything here is at peace. The story is still unfolding, still moving forward through deep time, carrying you gently with it. The ceratopsians demand more than a passing mention, because in their extraordinary evolutionary creativity they represent one of the most remarkable examples of anatomical diversification in the entire fossil record. The ceratopsian lineage began modestly enough. Early ceratopsians from the Jurassic and early Cretaceous of Asia were small animals, bipedal or partly bipedal, with only modest head ornamentation. Psittacosaurus, an early ceratopsian from the early Cretaceous of China, was roughly the size of a large dog, bipedal, with a parrot-like beak but no horns and only a very modest frill. It was clearly a successful and common animal, appearing in large numbers in early Cretaceous deposits, but it gives little hint of the spectacular forms that the later ceratopsian radiation would produce. As the Cretaceous progressed, and the ceratopsians diversified into the larger, more heavily ornamented forms of the late Cretaceous, they underwent one of the most rapid anatomical radiations in the history of large vertebrates. The diversity of horn and frill configurations that evolved within the ceratopsian lineage over a period of perhaps 20 million years is extraordinary. Every major late Cretaceous herbivore fauna in North America and Asia contains multiple ceratopsian species, each with its own distinctive combination of horn sizes and positions and frill shapes and frill decorations. What drove this explosive diversification of head ornamentation? The most compelling answer involves sexual selection and species recognition. In any animal community with multiple related species that occupy similar ecological niches, the ability to quickly and accurately identify members of your own species is critically important for successful reproduction. Mating with a member of a different species wastes reproductive effort. Natural selection therefore strongly favours the ability to identify conspecifics quickly and reliably. One of the most efficient ways to evolve this ability is through distinctive visual signals, features that are prominently displayed and clearly distinctive. Head ornamentation, horns and frills and crests, is ideal for this purpose because it is always visible. It faces forward where it can be seen approaching, and it can vary enormously between closely related species without affecting the animal's basic body plan or ecological function. Once sexual selection gets hold of a character like a horn or a frill, it tends to drive it toward extremes. The mechanism is straightforward. If females prefer males with more elaborate frills, or if males with larger horns win more contests for mating access, then the genes associated with more elaborate or larger ornamentation will be better represented in the next generation. Over many generations, the average frill becomes more elaborate, the average horn becomes larger, the variation between species becomes more pronounced. The process is self-reinforcing and can produce, within a relatively short evolutionary time, the extraordinary diversity we see in the late Cretaceous ceratopsians. Cosmoceratops richardsoni, from the late Cretaceous of what is now Utah, had 15 separate horn-like structures on its head, including 2 large brow horns, a small nose horn, and no fewer than 10 additional pointed projections around the margin of its frill. Its name means ornamented horned face, and it is well chosen. Styracosaurus albertensis had a frill dominated by 6 long spike-like projections extending outward from the frill margin, each potentially 2 or 3 feet long, creating a profile that would have been unmistakable and presumably highly visible to other Styracosaurus at a considerable distance. Torosaurus latus had one of the largest skulls of any known land animal, with a frill extending so far behind the skull that the total skull length sometimes exceeded 8 feet. These were not subtle differences. These were extravagant anatomical statements, evolutionary calligraphy in bone, each species writing its species identity in a distinctive script that other ceratopsians could read at a glance. Living alongside the ceratopsians in late Cretaceous North America were the hadrosaurs, and together these two groups formed the foundation of what may have been the most productively rich, large herbivore community the terrestrial world has ever supported. Imagine a late Cretaceous coastal plain in what is now Alberta, roughly 75 million years ago. The Western Interior Seaway is not far to the east, its shores only a few tens of miles away, the humid air carrying a faint marine quality even this far inland. The floodplain around you is dense with flowering plants, their blossoms adding splashes of colour to the green of the ferns, and the darker green of the conifer stands on slightly higher ground. The rivers that lace through this plain are slow and dark with tannins from the organic rich soils, their banks edged with dense riparian vegetation. The hadrosaur herds. There are many of them. They move in groups of dozens, sometimes hundreds, their movements raising clouds of insects from the flowering plants they push through, their crests occasionally producing those deep, resonant calls that travel through the humid air and echo back from the distant forest edge. The ground is soft with the moisture of recent rains, and their feet leave deep, clear impressions in the mud, each one the size of a large dinner plate, each one quickly filling with dark water from the high water table. From the forest margins, perhaps half a mile away, a group of ceratopsians is approaching the river to drink. 3 or 4 Pachyrhinosaurus, their nose bosses rough and angular, their frills modest by ceratopsian standards, but still broad and distinctively coloured. They move with the deliberate pace of large animals accustomed to being the best armoured creatures in their world, their broad feet planted with authority, their heads swinging slightly from side to side as they watch the hadrosaur herds and the forest margin simultaneously. Above all of this, in the late afternoon sky over the floodplain, several pterosaurs are circling on the thermals, their wingspans impressive from below, their shapes casting brief moving shadows on the ground when they pass between the sun and the earth. They are watching the river for fish, watching the ground for small animals exposed in the open floodplain. The slow circles are patient and efficient, requiring almost no energy expenditure in the rising warm air from the plain below. And somewhere in the forest, not visible from the open floodplain, a Daspletosaurus, a relative of Tyrannosaurus rex, is moving through the trees at the forest edge, its pace deliberate and unhurried, its head swinging, its deep-set eyes scanning the open ground ahead of it. This was the Cretaceous world, not a world of one spectacular animal but a world of extraordinary community, of dozens of large animal species interacting and competing and shaping each other through their ecological relationships. The most complex, most diverse, most productively magnificent large animal community in the history of life on land. And the dinosaurs were every part of it. The armoured dinosaurs of the Cretaceous, the ankylosaurs and the nodosaurs, were another expression of the period's evolutionary creativity, where the ceratopsians had invested in horns and frills as both offensive weapons and species recognition signals. The ankylosaurs had invested almost entirely in defence. Their bodies were covered in a mosaic of bony osteoderms embedded in the skin, overlapping and interlocking to form an articulated armour that protected the back, the flanks, the tail, and in some species even the eyelids, which had bony protective plates. Some ankylosaurs had broad triangular shoulder spines that would have made approaching from the front a hazardous proposition for any predator. Some had large lateral spines running down the flanks. Some had weaponized tails. Ankylosaurus magniventris, the largest and perhaps most familiar ankylosaur from the very latest Cretaceous of North America, carried a massive club at the end of its tail, formed by fused osteoderms. This club was not a passive defensive structure. Research on the musculature and bone structure of the tail indicates that Ankylosaurus could swing this club with considerable force, and force calculations suggest that a strike from the tail club of a large Ankylosaurus could have broken the lower leg bones of even a large Tyrannosaur. The Pachycephalosaurs, another distinctive Cretaceous dinosaur group, took a different anatomical approach. These were bipedal dinosaurs with enormously thickened skull roofs, domes of solid bone sometimes over 10 inches thick, which have been interpreted as being used in head-butting contests between males competing for social dominance or mating access. The bone in these dome skulls shows microstructural features consistent with repeated, high-impact loading, consistent with the hypothesis of dome-head combat. Some species had elaborate arrangements of spikes and knobs around the margin of the dome that may have added to the visual display, or added cushioning to glancing impacts. The late Cretaceous world contained more large dinosaur species, more ecological complexity among its large animals, and more behavioural sophistication in those animals than any earlier period in Earth's history. And all of it was still only the backdrop to the story's next chapter. The feathered dinosaurs of the Cretaceous world represent one of the most extraordinary revelations in the history of paleontology, and their discovery has fundamentally changed the way we understand the relationship between the living and the extinct. For most of the 20th century, dinosaurs were understood as essentially reptilian animals, scaly-skinned, cold-blooded, relatively slow-moving, fundamentally different in their biology from the warm-blooded birds and mammals that came after them. This view was not unreasonable given the evidence available. Dinosaur fossils, for all their magnificence, usually preserve only bone. Skin impressions from large dinosaurs did show scale-like textures in many cases, and the very word dinosaur, from the Greek for terrible lizard, encoded an assumption of reptilian nature that took decades of accumulated contrary evidence to dislodge. The dislodging began in earnest in the 1990s, when an extraordinary series of discoveries from the early Cretaceous Yixian and Jiufotang formations of Liaoning province in northeastern China began revealing dinosaur fossils preserved in a fine-grained volcanic ash that captured not just bones but soft tissues, feathers. The impressions and sometimes the actual carbonized remains of feathers preserved in extraordinary detail around the bones of animals that were clearly dinosaurs. The first and perhaps most famous of these discoveries was Sinosauropteryx, a compsognathid theropod roughly 3 feet long that was covered in a dense coat of simple filamentous feathers. Not flight feathers, not the complex asymmetric feathers of flying birds, just simple structures, more like the soft, fluffy down of a modern chick than the structured veins of a flight feather, covering the animal's body in a coat that would have provided substantial insulation. Sinosauropteryx was not flying, it was keeping warm. The implications were profound. Simple filamentous feathers serve primarily as insulation. Insulation is an adaptation for animals that generate their own body heat and need to retain it. Sinosauropteryx feathers were therefore strong evidence that this animal was endothermic, warm-blooded in the common parlance, generating its own body heat internally rather than relying on the sun. And if Sinosauropteryx was warm-blooded, then the common ancestor of Sinosauropteryx and all other theropods was probably warm-blooded too, which meant the theropod lineage as a whole was probably warm-blooded, which meant a major branch of the dinosaur family tree was running warm. Subsequent discoveries deepened the picture. Dilongparadoxus was a small tyrannosauroid from the same Liaoning deposits that bore simple filamentous feathers. This was a primitive relative of the tyrannosaur lineage, suggesting that the entire tyrannosaur family, including the massive Tyrannosaurus rex of the late Cretaceous, descended from feathered ancestors. Eutyrannus huali, described earlier, was a much larger tyrannosaur relative, approaching 30 feet in length, also bearing long filamentous feathers. Feathers on a 30-foot predator. Microraptor had flight feathers on all 4 limbs, the long vanned feathers of the wing arranged on both the arms and the legs, creating an animal with 4 functional wing surfaces. Microraptor was capable of gliding, and possibly of limited-powered flight, and the study of its feathers and wing geometry has produced extraordinary insights into the early evolution of avian flight, suggesting that the transition from ground-running dinosaur to fully aerial bird may have proceeded through a 4-winged tree-climbing intermediate stage. Anchionis huxleyi, named for the great Victorian biologist Thomas Huxley, who was among the first to recognize the evolutionary connection between birds and dinosaurs, was a small feathered dinosaur whose feathers were preserved in sufficient detail that chemical analysis could reveal the melanosomes, the pigment-containing structures that give feathers their color. The analysis showed that Anchionis had black and white patterning on its wings with a reddish-orange crest. This is the coloration of an animal that had never been seen by any human eye, reconstructed from the chemistry of feather remnants preserved in 75-million-year-old rock. The color of a Cretaceous world, returned to visibility by the patience and ingenuity of modern science. The Cretaceous world, through these feathered dinosaurs and early birds, was a world of colours and sounds that we can only partially reconstruct. The colour-producing structures in bird feathers today suggest that Cretaceous theropods may have displayed colours across a wide spectrum, from simple blacks and whites and browns to the kind of structural iridescences that produce the brilliant blues and greens of peacock feathers and hummingbird plumage. A Cretaceous forest would have been, in its bird and feathered dinosaur inhabitants, a world of living colour, displayed for purposes of species recognition and sexual selection and territorial advertisement in ways that the bone record alone could never have revealed. The sounds of the Cretaceous world deserve extended consideration. We tend, when we imagine the dinosaur world, to populate it with the sounds we associate with large reptiles in the modern world, the hisses and growls and occasional bellows of crocodilians, perhaps amplified to match the larger body sizes of the Cretaceous giants. But this may be profoundly wrong. The evidence from the hadrosaur crests we have already discussed suggests deep resonant low-frequency calls. The evidence from the neural anatomy of some dinosaurs suggests well-developed auditory processing, capable of discriminating sounds with the sophistication we associate with birds and mammals, rather than the simpler auditory systems of most modern reptiles. The birds that were evolving through the Cretaceous were developing vocal communication systems that would eventually produce the extraordinary acoustic world of modern birds. The earliest birds may have been capable of some form of song, or at least of complex calls that conveyed information about identity, territory, and status. The small feathered theropods, many of them closely related to the bird lineage, may have been capable of similar acoustic communication. The Cretaceous world probably sounded richer, more layered, more acoustically complex than we generally imagine when we think of dinosaurs. Not the occasional roar of a massive predator moving through a largely silent landscape. A world full of calls and songs and responses, of acoustic territories and acoustic signals, of the dawn chorus beginning each morning with dozens or hundreds of voices, some recognizable as early birds, some belonging to animals whose calls we have no modern analogue for. The small mammals of the Cretaceous contributed their own dimension to this world. Cretaceous mammals, despite their small size and their subordinate ecological position, were not simple creatures. Their brains, relative to body size, were larger than those of most Cretaceous reptiles. Their sensory systems were sophisticated. Their teeth were complex, capable of precise, multi-stage food processing that reptile teeth generally cannot achieve. Their reproductive systems were diversifying, with some lineages already moving toward the live birth and extensive parental investment that characterize the therian mammals, the group that includes all modern marsupials and placental mammals. Some Cretaceous mammals were achieving ecological roles more significant than we once appreciated. Repenomamus robustus, from the early Cretaceous of China, was a surprisingly large mammal for its time, reaching perhaps 3 feet in length, and stomach contents preserved in one specimen contained the bones of a small dinosaur. Repenomamus was not just an insectivore hiding from dinosaurs, it was eating them. The small mammals of the Cretaceous were more ecologically varied and more behaviorally complex than the simple picture of helpless, cowering, exclusively nocturnal insectivores that was once standard. The turtles and lizards and early snakes of the Cretaceous world add further texture. Turtles have one of the most ancient lineages of any living reptile group, their basic body plan established in the Triassic, and essentially unchanged since. Cretaceous turtles were diverse, and included both aquatic and terrestrial forms. Some were enormous by modern standards. Archelon, from the late Cretaceous marine deposits of what is now Kansas, was a sea turtle approaching 14 feet in length, the largest turtle known from any period of Earth's history. It moved through the warm, shallow seas of the western interior seaway with the slow, patient efficiency of a large, buoyant marine reptile, feeding on jellyfish and soft-bodied prey. The lizards of the Cretaceous were diverse and ecologically important components of every terrestrial ecosystem. They filled small carnivore and insectivore niches. They occupied the scavenger role at small body sizes. They climbed and burrowed and swam and ran with the versatility that has made the lizard grade of organization one of the most persistently successful in the history of tetrapod life. Early snakes, appearing in the Cretaceous, were beginning their own extraordinary diversification, their limbless body plan proving remarkably versatile for moving through substrate and vegetation that limbed animals could not easily navigate. All of these animals, from the enormous marine turtles to the tiny Cretaceous mammals, to the small agile lizards to the feathered theropods, to the great herds of hadrosaurs and ceratopsians, were part of a single, integrated, extraordinarily complex ecosystem. An ecosystem that had been building in complexity for 140 million years since the first small dinosaurs began their quiet colonization of the post-Carnian world. The Cretaceous was the culmination of that building process, the most complex terrestrial system Earth had produced, the most diverse array of large animals, the most sophisticated food webs, the most elaborately co-evolved plant-animal communities. And through all of it, holding it together, shaping it by their presence and their needs and their deaths, were the dinosaurs. The geological forces shaping the late Cretaceous world were doing more than simply maintaining background stress. They were, in some regions, dramatically restructuring the physical geography in ways that created new evolutionary opportunities, even as they closed others. The most dramatic of these restructuring events was the regression of the Great Shallow Seas. Through much of the Cretaceous period, vast areas of the continental interiors had been covered by shallow epiric seas, inland extensions of the ocean that spread across low-lying continental regions when sea levels were high. The western interior seaway of North America, which at its maximum had divided the continent from the Gulf of Mexico to the Arctic Ocean, was the most spectacular example. These seas had been among the most productive marine environments on Earth, their warm shallow waters teeming with life, their shores lined with the dense coastal forests where the great dinosaur faunas flourished. As the late Cretaceous progressed toward its final chapter, these seas began to withdraw. Sea levels dropped, gradually and with fluctuations, but with a general downward trend that slowly exposed the seafloor as new land. The western interior seaway narrowed. The connection between its northern and southern arms weakened. Land animals that had been separated by the sea for millions of years began to recontact each other across the narrowing divide. This seaway regression had complex effects on dinosaur evolution in North America. The reconnection of Larimedia and Appalachia, the western and eastern land masses that had been separated by the seaway, allowed species that had been evolving in isolation to come into contact again. This contact could produce new competitive relationships, new opportunities for hybridization, new ecological dynamics. The late Cretaceous North American dinosaur fauna shows evidence of this complexity in the variety of ceratopsian and hadrosaur species present in the latest deposits. The Deccan Traps volcanism, centered in what is now the Deccan Plateau of India, was also influencing the latest Cretaceous world in ways that were more subtle, but ecologically real. The Deccan eruptions, which had been building through the last million years or so of the Cretaceous, were producing pulses of volcanic gas that affected the global climate. Carbon dioxide from the eruptions was warming the climate somewhat, and the warming was changing the distribution of plant communities, shifting the ranges of dinosaur populations, altering the productivity of ecosystems in ways that the fossil record captures in its changing species compositions. Some researchers have argued that the Deccan volcanism was already stressing the dinosaur communities of the late Cretaceous before the asteroid impact, creating a world that was less robust, less diverse, less able to absorb additional shocks than it had been a few million years earlier. Others have argued that the late Cretaceous dinosaur fauna was healthy and diverse right up to the moment of the impact, with no meaningful pre-impact decline. The debate continues, and the fossil record, which is inevitably incomplete and geographically patchy, does not yet provide a definitive resolution. What we can say is that the late Cretaceous world, whatever stresses it was experiencing from volcanism and sea level change, was still genuinely magnificent in its animal life. The last tyrannosaurs were among the most powerful and sophisticated predators the planet had ever produced. Tyrannosaurus rex, the last and largest of the North American tyrannosaur lineage, was in many ways the culmination of 100 million years of theropod evolution. The features we associate with it, the enormous skull, the tiny arms, the massively muscled hindquarters, the forward-facing eyes, were not accidents or arbitrary configurations. They were the products of millions of generations of selection for a very specific ecological role, the apex predator of a rich, diverse, high-productivity herbivore community. The forward-facing eyes of Tyrannosaurus rex gave it binocular vision, the overlapping field of view that allows precise depth perception. This is the visual configuration of predators, the same arrangement we see in owls and hawks and humans, animals that need to judge distances accurately when pursuing or ambushing prey. The binocular field of view of Tyrannosaurus rex has been calculated to be wider than that of modern hawks, suggesting that its depth perception was among the best of any terrestrial animal its size. Its olfactory bulbs, the parts of the brain responsible for processing smell, were proportionally enormous, suggesting a sense of smell comparable to or exceeding that of modern vultures, which can detect carrion from miles away. A tyrannosaur moving through the late Cretaceous forest would have been able to smell prey and carrion, and the scent trails of other tyrannosaurs at ranges we can barely imagine, processing olfactory information with the sophistication we associate with the most smell-dependent of modern mammals. Its hearing was almost certainly acute. The cochlea, the hearing structure of the inner ear, when reconstructed from tyrannosaur braincase anatomy, suggests sensitivity to low-frequency sound, the kind of deep, travelling sound that carries information over long distances in forested environments. Tyrannosaurus rex was, in its final fully evolved form, a sensory predator as much as a physical one. Its enormous body gave it the power and mass to subdue the largest prey animals in its world. Its exceptional senses gave it the ability to find that prey and to monitor its environment for other tyrannosaurs, and for the social information that, we now believe, characterized the lives of these animals. There is growing evidence that tyrannosaurs were not solitary hunters, as the classic popular image suggests. Some fossil sites preserve multiple tyrannosaur individuals apparently dying together, which could indicate group behavior. Trackways preserving the footprints of multiple large theropods moving in the same direction at roughly the same time have been interpreted as evidence for coordinated movement. The possibility that tyrannosaurs lived in family groups or loose social associations, communicated with each other, cooperated in some contexts, is now taken seriously by researchers who study them. If tyrannosaurs were social, and the evidence is suggestive though not conclusive, then the picture of the late Cretaceous world becomes even richer. Not just giant solitary predators moving through a landscape of prey, but complex social animals with individual relationships, with communication systems, with the kinds of behavioral sophistication that we see in modern, large predators like wolves and lions. The last Tyrannosaurus rex individuals to walk the earth were animals of this sophistication, moving through the Montana and Alberta forests and floodplains of the very latest Cretaceous, hunting the last ceratopsian herds and the last hadrosaur groups, producing the footprints and the bones that we now find in the rocks of the Hell Creek Formation, and know as the final chapter of the non-avian dinosaur story. They did not know it was the final chapter. How could they? They were simply living, as their ancestors had been living for 165 million years, as their descendants, the birds, would continue to live for 66 million more years and counting. Simply living in the most extraordinary dynasty land life has ever produced. The last ordinary day was ordinary all the way to its end. And then the sky changed. The legacy of the dinosaurs in the living world extends far deeper than the birds, though the birds are the most obvious and most vivid part of it. Consider the soil. The soils of the modern world are the product of hundreds of millions of years of biological activity, and the Mesozoic contribution to that history was immense. The dinosaur era's forests, the great conifer forests of the Jurassic, and the increasingly angiosperm-dominated forests of the Cretaceous, contributed hundreds of millions of years of organic matter to the developing soils of the continents. Root exudates and fungal networks and falling leaves, and the dung of enormous herbivores and the corpses of animals killed and consumed and decomposed all contributed to building the biological richness of the soil systems that persist today. Every time a gardener digs in soil and marvels at its dark richness, at the visible evidence of biological complexity in a handful of earth, they are holding the accumulated biological heritage of hundreds of millions of years of terrestrial life. The Mesozoic, the dinosaur era, is a major chapter in that heritage. Consider the forests. The conifer families that dominate many of the world's forest ecosystems today, the pines and firs and spruces and redwoods and their relatives, trace their origins to the Triassic and Jurassic radiations that occurred during and after the Carnian pluvial episode. These trees, which today carpet the northern hemisphere in vast boreal forests and populate temperate mountain ranges around the world, are living links to the dinosaur world. The redwood trees of coastal California and the giant sequoias of the Sierra Nevada are members of a lineage that was already ancient when the last tyrannosaur walked the earth. Standing beneath a giant sequoia, looking up at a trunk that may have been growing for 2,000 years, you're standing beneath a tree whose family has been growing on this continent since the age of the dinosaurs. Consider the flowering plants. The angiosperms, whose early Cretaceous appearance transformed the terrestrial world, and drove the evolutionary explosion of the late Cretaceous, have now become the dominant plant group on Earth, comprising roughly 90% of all plant species. Every flower you have ever seen, every fruit you have ever eaten, every crop plant that forms the foundation of human agriculture, belongs to a lineage that evolved and diversified during the dinosaur era, shaped in part by its co-evolutionary relationships with the dinosaurs that ate its fruits and spread its seeds and browsed its foliage. The apple you might eat for breakfast traces its fruit design to the co-evolutionary relationships between early angiosperms and Cretaceous animals. The wheat that feeds more humans than any other single crop has its root system and its metabolic chemistry built on biological foundations laid down during the Cretaceous and earlier. The tomato and the potato and the rice and the corn, all of them are products of evolutionary lineages that stretch back into the dinosaur world. Consider the insects. The insects of the modern world, the most species-diverse group of animals on Earth, underwent much of their diversification during the Mesozoic. The beetles, with their more than 400,000 described species, began their extraordinary radiation during and after the Carnian pluvial episode. The bees and wasps and ants that dominate modern insect communities co-evolved with the flowering plants of the Cretaceous. The butterflies and moths are Cretaceous innovations. The flies that are essential decomposers in every modern ecosystem were diversifying through the Jurassic and Cretaceous in close relationship with the dinosaur communities that provided them with food. When you see a bee visiting a flower, you're seeing the product of a co-evolutionary relationship that began in the Cretaceous. When you see a beetle in the garden, you are seeing a member of a lineage whose diversification was driven in part by the forests and dung piles of the dinosaur world. When you hear a fly, you are hearing the descendant of Jurassic and Cretaceous forms that were processing the organic matter of the dinosaur ecosystems into nutrients for those ecosystems' continued productivity. Consider the birds. We have already established that birds are dinosaurs, in the strict technical sense. But the full scale of bird diversity and abundance in the modern world is worth appreciating in the context of the dinosaur legacy. There are approximately 10,000 species of birds alive today. They have a combined biomass that exceeds that of all wild mammals on Earth. They inhabit every continent and every biome, from tropical rainforests to polar ice sheets, from alpine peaks to ocean depths. They perform ecological functions of enormous importance: pollination, seed dispersal, insect control, scavenging, nutrient cycling through their droppings, and many others. The world without birds would be a profoundly impoverished and functionally compromised world. All 10,000 species of living birds trace their ancestry to a single lineage of small theropod dinosaurs that survived the end Cretaceous extinction. All their extraordinary diversity, every form from the ostrich to the hummingbird to the penguin to the albatross, evolved after that survival. The entire modern bird world is the product of 66 million years of evolution from those few surviving lineages. When you see a bird in the morning light, you are seeing the continuing expression of the dinosaur lineage's evolutionary creativity. The same creativity that produced the sauropods and the ceratopsians and the tyrannosaurs is still working, still experimenting, still producing new forms and new adaptations in the birds that inhabit every corner of the living world. The dinosaurs are not gone. They have never been gone. They survived the end Cretaceous extinction in the most fundamental biological sense, through their descendants. The lineage continues. The empire, transformed beyond recognition from its Cretaceous expression but genetically and biologically continuous with it, is still the most successful group of large animals on the planet. When you appreciate this, when you truly hold it in your mind, the story of the dinosaurs changes its emotional register. It stops being a story about magnificent creatures that flourished and then were destroyed. It becomes a story about a lineage of extraordinary animals that has been continuously present on Earth for 234 million years, and that is present right now, in every bird you can see and hear, alive and flying and singing in the world outside your window. The story of the dinosaurs is not over, it is not even close to over. It is ongoing. The most successful land animal dynasty in Earth's history is still with us. And that is perhaps the most extraordinary thing about this whole extraordinary story. 234 million years ago, a small, quick, bipedal animal in the margins of the Triassic world survived the rain. It survived the extinction. It diversified. It filled the world. It built the most magnificent biological empire the terrestrial world has ever seen. And then it survived the end of its own empire in the bodies of the small, feathered, flying descendants that carried its genetic heritage through the darkness and the cold and the impact winter and into the new world beyond. And it is still here, right now, singing. Listen. In the darkness, in the quiet of wherever you are resting tonight, in the gap between one breath and the next, there is a world outside. And in that world, in the trees and on the rooftops and along the water margins and across the open fields and high in the cold air above everything, the descendants of the dinosaurs are living their lives. They have been doing so without interruption for 234 million years. The rain began. The world changed. The small animals in the margins became the rulers of the earth. The rulers became the most magnificent dynasty land life has produced. The dynasty ended and continued and transformed, and is still, right now, today, at this moment, alive in the world. That is the story of the dinosaurs. That is one of the most beautiful stories this planet has ever told. And you've been carried through all of it, through 234 million years of life and transformation and resilience and wonder, in the quiet dark of a night that is still and peaceful and perfectly safe. Rest now. You are part of this story too. The universe that made the dinosaurs made you. The planet that supported them supports you. The air they breathed, the water they drank, the elements they were made of, you are made of those same things. In the deep chemical sense, you and the tyrannosaur are relatives, products of the same 4.5 billion years of planetary history, the same processes, the same elements, the same extraordinary coincidence of conditions that makes a planet like this one possible. You belong to the same story. And tonight, you are resting in it. Sleep well. Dream of ancient things. The dinosaurs are at peace, and the birds are dreaming in the trees, and the world outside is quiet and dark and full of the deep, accumulated presence of all that time. Thank you so much for watching. If you enjoyed this journey through 165 million years of the most extraordinary animal dynasty in the history of life on land, please consider leaving a like and subscribing to the channel. It really does help us continue making more content like this. More long, quiet journeys through deep time, more ancient worlds, and the extraordinary lives that filled them. Anyways, see you in the next one. The story's ending now. Not abruptly. Not with any sudden sound or sharp transition. Simply, the way evening light fades from the highest edge of the sky, gradually, gently, the brightness softening and the colour deepening until the world is dark and still and resting. Let the images of all those ancient worlds begin slowly to settle. Let the great sauropods of the Jurassic lower their long necks and find their resting places in the deep shade of the ancient conifers. Let the enormous footsteps slow and stop. Let the forests grow quiet around them, the only sounds the wind and the slow drip of water from leaves and the distant calling of something small and feathered high in the canopy. Let the hadrosaur herds of the late Cretaceous find the clearings where they rest. Their bodies warm in the cooling evening air, their crests silent now, the resonant calls that carried across the afternoon forests replaced by the quiet sounds of large animals breathing slowly in the dark. Let the tyrannosaur find its resting place in the deep forest, its massive body at ease, its senses still awake but no longer actively hunting, just present, just existing in the warm and fragrant darkness of the late Cretaceous night. Let the last evening of the last full day of the dinosaur era settle over everything. The October sky in the Montana forest deepening to purple, and then to the rich dark blue of a sky with no light pollution, no civilization, no human presence to interrupt the immense unbroken vault of stars above. Let it all rest. You have travelled an extraordinary distance tonight. Further than any spacecraft, deeper than any geological survey. You have stood in the wet forests of the post-Carnian Triassic and watched the first dinosaurs move with quick, uncertain energy through the undergrowth. You have heard the ground shake under the Jurassic sauropod herds and felt the deep